the semantic segmentation task, which typically happens in many biomedical imaging. Okay, so first 30 minutes or so we will try to look at what is this new semi-supervised method, and then we will switch to how we apply that to a medical image segmentation. Okay, so we have all seen what is supervised learning. You have a data and you have the corresponding labels, and you try to train it with that labels. So you have for example tumor detection. You give a patch and try to identify it as whether it's a malignant or a benign part, or you give a microscope slide and see if there is a infection or not. Many such things, right? So that is supervised learning. Unsupervised learning is, so supervised learning is with a teacher. There is somebody who is telling you what is the expected outcome, what you are supposed to do. So this is the input and this is the corresponding output, and this is what you need. On the contrary, unsupervised learning is something where there is no target. You just keep on exploring lot of data and try to come up with something which is either a data abstraction or a data clustering or many different things. So that's unsupervised learning. So the semi-supervised is kind of something in between. So supervised methods, I think it is pretty clear. You have some image and you have to figure out what the image is. So you give this image, it should say it's a rocket. You give this, it should say a boat, and so on, right? So this is a vehicle, craft, something like that. So these are like different. So you will have this, what is called as the label for the image in the data. Now semi-supervised is where you get some supervision, and at times sometimes you are on your own, you don't know what it is. So this is when we work in medical domain. This happens generally with the medical data. So you have a lot of medical data, and often you don't have what is called as the labeling. So because how do you prepare a full data set? Let's say you are trying to get, so we were working on a problem which is called fundus images. So retinal images, you take it through a special camera, you can image your retina, and the idea, so many of you might have heard this, a diabetic retinopathy. So somebody has to label, sit and look at every image. There are like very fine details happening in there. So a doctor only will be able to label. I mean, we won't be able to label ourselves. So they will go and say, okay, this belongs to diabetic retinopathy of this particular grade, grade 1, grade 2, grade 3, etc. So this labeling require a lot of expertise. Or even if it's a cancerous tissue, you need to really go in detail, because different tissues look different, and the characteristics of malignancy can be different. You really have to have an expert doctor sitting in, looking every patch to identify which is which is a malignant part and which is a benign part. So this labeling is costly, whereas acquiring the image is many times not that costly. Okay, so you typically, I mean, this is our experience also. We were approaching a pathologist for some of these cytology images, and what we found is that they can give us like lot of images, hundreds of images, and the point is we don't have labels for them. So that's the setting of semi-supervised learning. So the doctor will be able to sit with you and give you labels of 100 images or 200 images. Rest of the data is not labeled, right? So that is the setting of semi-supervised learning. You have medical image which is partially labeled. Now, is the all other data is useful or not without label? Without label, traditionally we can't train that. Okay, so that's the semi-supervised learning. Okay, this much is clear. So it's about doing that. We have some set of labeled images, some set of unlabeled images, and how do we use this unlabeled images in learning something useful. Okay, so there are few assumptions here. So, okay, let me tell you what this picture means. This is just trying to separate two classes. So, these are the orange class and the blue class. Now, I don't have all these points in the training data. This is actually all the possible images, let us say. But I have only very few data which is labeled. So, this 3 triangles is what I have labeled from the actual orange class, and this 2 samples from the blue class is labeled. So, if I were to train a conventional supervised thing, it will try to look only at this 3 and this 2, and it will try to somehow draw a line between them, which is separating those 2. Correct, no? Now, of course, that's one way of doing it, but then I also have all these in between points. Of course, I don't know its color, but I also have all these points. Now, SSL tried to assume a certain things about the data to come up with a better separation between those 2. So, this entire thing is training data, but I only have labels for this 2. So, what are the assumptions? The assumption is that the data is having a smooth distribution, which generally means the following. If you have a point here, the point which is very next to it will most likely have the same label. So, if I have an orange point which is this triangle, these immediate next things will have the same orange color. That's one assumption. Then the other assumption is you have a plus which is blue color here. The immediate things will have blue color. Okay, so that's about this first assumption. Then it's about a low density decision boundary. The decision boundary won't pass through too many points. It won't cut too many points. It is supposed to be passing through a low density region. It will cut minimum number of points. And then there is a third thing which is called manifold assumption, which is illustrated here. If you think all these are becoming part of an arc, most of the class which correspond to that particular class will be same kind of the manifold. So, that's a more technical assumption. We don't really do too much about this. Let's mostly concentrate on this. Okay. Now, based on this, again, we don't know how to train our neural network to do this, but we discuss a couple of methods in putting these things into action. Okay, so that's our agenda. There are like too many ways to do it. We will only discuss 3 or 4 things. Okay. So, how do we do smoothness assumption? So, those are the 2 things we said we will do: smoothness assumption and low density assumption. Okay. So, how do we do SSL in practice? Okay, so this is from the standpoint of a neural network now. Okay. So, how do we incorporate smoothness assumption? You have a lot of points. Now, the smoothness assumption says that the neighboring points will belong to the same class. Okay. So, what you do? You try to sample neighboring points. You have a data and you try to predict its output, and you generate a point which is its neighbor. How do you generate a point which is its neighbor? You just add some noise to it, very small amount of noise. You have an image, you add a little bit small noise to it, it is a neighboring point, and you predict that output. Those 2 outputs should be exactly the same. Do we get the point? So, if it's a neural network, it's a neural network, and those 2 outputs should be the same. So, how do we make it same? We define some loss function and try to minimize that particular loss function. Is that okay? Now, the low density boundaries, that's also in a similar method. So, small changes in the boundary should not matter. You have a boundary, and even if you change the boundary a little bit, it should give you the same classification result. How do we ensure that? You have the model, you kind of look at the neighboring models. What is a neighboring model? The model, either you put a little bit drops few things, or you change the weights a little bit. So there are many ways of sampling these models. So you try to push the model little bit that side, this side, the model should still give you the same exact result. So those are two things which we generally do in SSL. Okay, so I'll give you a couple of examples and then we will go into the applications of the thing. Okay, so let me look at this. These are the probably most earliest attempts to do this. So this is there are two models which was proposed, which is called as the pi model and the temporal ensembling. So the pi model is what we said as the perturbing the data. You have a point and you try to push the point. The data you push it this side, that side, it should give you the same output. Okay. So this is actually the pi model. So you get a label and you get a image. Generally, if those two are there, you just pass through the model and you can train with a cross entropy. You update the weights with a cross entropy. This is the labeled data. Now you have unlabeled data, which you don't know what is the label. So you cannot train it with a cross entropy. What you do is, you take the image, you try to make different augmentations. You take, let's say you add a little bit of noise, or you try to shift it slightly, 5 pixels you shift, or you rotate it by 4 degrees, or such things. I mean, these are called augmentations, right? We use it when we train to make the network robust. So you apply those randomly some augmentations and generate two outputs. One is the image as such and one is the image which is augmented. So you get two outputs, and according to our smoothness assumption, those two outputs should be the same. It should be the same. So you try to minimize the square distance between the two outputs. You have like 0, 1s as a vector coming at the output. So you train it with the mean square loss, and your total loss is going to be the some kind of weighted sum between those two. So this is the pi model. This is actually perturbing the data to make a robust model. So you use labeled data for doing this and unlabeled data for doing this. Okay. A temporal ensembling is again with some the other thing where you actually try to look at different models. Okay. Now we don't in this, at least in this example, you don't actually take the model and add noise to it. What you do is, you are training, right? You have a every iteration you are updating the weights. So you take the past 4 or 5 different weights which you have while training. So I have the whole data. I put one batch of data, I update the weight. I put the second batch of data, I update the weight. Third batch. So you are getting sequentially all these models which are only differing by a little bit small update in the gradient descent. So you take all those 5 models and you try to find one of the what is called as a pseudo label. You have a model, you have past 4 models, you give the current batch, you predict it. You predict it using the previous model, you will get a previous prediction, previous prediction. Like that you get 4 or 5 predictions. You average all the 5 predictions, you get a value, and that you treat it as your label. Okay, so that's your label. And then each of these prediction of all the models, it should be same as that. Because the model only changed a little bit because you only had 3 or 4 batches. So all these should be same. So you train it with again the mean square error between those two outputs. Those two outputs should be the same. You update the derivative and train it. Okay. Yeah, I'll probably cover this. So the problem with this moving average of this model, sir, you need to keep a lot of models in the memory and keep on averaging those outputs, etc. So this is a slightly improved version of that. There are two different networks. One is called as a student model and one is called as a teacher model. So what you do is, okay, of course, if you have labels, you just try to do cross entropy training. But if you don't have labels, what you do is, so you keep another model which is averaged over the past 3 or 4 models. So you predict from both of them and try to see if their output is the same. So you try to do that thing. So that is typically the mean square error. All this consistency cost is what is actually the mean square error. Okay. Yeah, I'll probably skip one or two. This is another thing. This is a virtual adversarial training. So what you do is, I said you perturb the data with some random noise. Now, you don't try to perturb it with random noise, you try to perturb it with a very adversarial noise. Okay, what is adversarial noise? So your noise can be anything. Let's say I have this vector. So input is a vector, right? I mean, you have a vector with some numbers as the features. Now you can add noise to anything. Let's say I'm adding a 0.01 to here, another 0.01 to here, let's say 0.003 to here. I mean, there are many ways to add random noise here. Now what is adversarial noise? Adversarial noise is, so this is just another vector, right? Another vector of very small values. Now this noise, when is it adversarial? It is adversarial when this is such that with a very small value of the noise itself, the output flips, and that happens in neural network. Okay, neural networks are very sensitive to this kind of very particular directions of noise. So that's known as the adversarial noise. So how do you find it? Once you have a neural network, you can try to see the derivative of the output with respect to all these input values, and you can see where the derivative is maximum. That particular vector is the adversarial noise. So you try to train it, perturb it with adversarial noise, not just any noise, and then you need to train with the unlabeled data where those two outputs are same. The input, when you get one output, the input perturbed with the adversarial noise, you get another output. So these two outputs needs to be same, and you try to minimize the mean square error there. So that's virtual adversarial training. I'll skip this, and there are two methods which I wanted to discuss. These two are the ones which we used. Therefore, both of these are from Google actually. They did it around 5-6 years back. This one and the next one also very close to it. So here, what they do is they do what is called as a mix match. What you do? You generate these pseudo labels from many augmentations. So you have one input that you need to actually get the you need to train with this unlabeled input. I don't know whether this is car or bus or anything. So you get this input, you try to make a lot of augmentations. One is the car here, one is its flipped version, maybe a rotated version, everything. So you get some prediction, some probability at the output. And you kind of average all those probabilities and try to do something like a softmax. So your maximum will get pushed up, and then all the other things will go down. And you take this and try to do a mean square error between this and these individual outputs. Okay, so you do a lot of them in one go. So it's a k different augmentation. So that is what is there called as a mix match. Okay. Now there is a fixed match also. It's again this is the next year after they proposed to mix match. They tried to change something and tried to look at these things. So you have again a data which is not having a label. You try to do a weakly augmentation, you get some output, and you do a strong augmentation and get output, and these two outputs should be the same. Here you do a sharpening, you do a softmax kind of transform. So you need this to be very much same. These two things should be the same. So this is typically a mean square error between those two outputs. So the weak augmentations are just flipping or shifting, which doesn't affect the image too much. And the strong augmentation is you shear it, you do a color transform, you add a lot of noise, all these things. So this is what fixed match does. Okay. Okay. So generally we were telling we have the option of perturb the model or perturb the data. I think perturb the data we saw mix match and fixed match. That is the final two things we saw. And we saw this pi model and mean teacher when we have the perturbation of the model. So that's the idea of semi-supervised learning. Okay, I'll quickly go through what is semantic segmentation. Some of you might know already, but because if anybody is there who doesn't know what is semantic segmentation, this is useful. So what is semantic segmentation? It is about, earlier you had only one object in the image. Now you have many objects and you need to label each object and find out where it is. So for example, this is a traffic scene. You need to figure out that this is a car, that's a road, and this is some trees, this is the sky, and I mean you get the idea. This is the building, and so on and so forth. So you need to label each and every point in the image. So you need to have class labels for every point. Earlier you had only one class label. Now if you have a 100 cross 100 image, you will have 10,000 class labels for each pixel. So of course, I mean other than lot of other things, it is useful for medical images, telling which of these cells are actually malignant. That is what we were working on. Okay. Yeah. So how do you actually measure how good it is? So we measure using many different things. Okay. So precision is precision recall is standard detection kind of thing. I'll just tell what is precision. So you have a lot of area which is malignant, and sorry, yeah, that's recall. Let me tell you what is recall. Recall is basically, let's say you have this whole area which is malignant. Out of that, how much did you actually detect as actual malignant area? So that is recall. So you had so much initially and you took back as some of them, that is recall. Precision is the other way. You have detected let's say some 100 parts as the malignant part. Out of this 100, how much is actually malignant? That is your precision. And this is some kind of average between the two. Okay, so we will only be concentrating on that. So how do we do the semantic segmentation? So generally we have convolutional layers followed by fully connected layers. People know this, right? It's a convolutional neural network. So segmentation, one way is you take small patches and try to figure out what is there. So this is actually trying to detect the cat probability for smaller patches of this image, and you see it is roughly around here, and it doesn't help much. So what people have come up with is these deconvolutional layers. It's a layer which is kind of up convolution. So this is the general neural networks work like this. So you have a convolutional encoder kind of thing, and then there is a decoder which comes up here. So, and one of the things which is very famous is this UNet, just a architecture. So this was originally introduced to actually segment some of these cell images from the microscope. So this is kind of the input and this is the kind of label. So it's some particular cell which is segmented from the microscopic image. So there are of course much more bigger networks which is being proposed. I'll skip that anyway. So what did we work on? We were working on looking at identifying malignant clusters of these cells. So this is a cytology image. People have prepared that slide, and it is under microscope and trying to figure that out. So generally at full resolution things look like this, and it is easy to actually identify, okay, this is a malignant cell. So these are the corresponding labels. The red part is basically the malignant cell, and the blue part is basically benign cells, and then it's a background, and the green part is basically the cytoplasm of the cell. Okay, so this is what is expected. Okay, now this is we can still do it. I mean, you can have these images and try to label these things and try to actually come up with, try to train the neural network. But when we get to low resolution things, it was almost impossible to actually do this kind of labeling. Okay, and this was taking a lot of time. Well, even this took a lot of time, but this was almost next to impossible in doing this. Okay, now why do we need this low resolution labeling? Is because these scanners, the slide scanners, they are very slow typically. Now the idea is you do a scan at a low resolution, it is faster. So you try to figure out where is the malignant area and then try to get that area at a higher resolution. That was the motivation behind this work. So that people can confirm that in a high resolution. Lower resolution, you suspect some malignant areas and then come back and kind of verify it in the high resolution area. So this was the problem that we worked on. So we kind of collected lot of data at different resolutions, and it was around 400 cross 400 patches, and this was the higher 40x resolution. Slightly smaller resolution will look like this. This is very small resolution. So we tried to work with this 4x resolution and 400 cross 400 image patches. So of course labeling, as I told, is manually intensive, and we need to confirm this whole thing with the doctor. I mean, I cannot just say this is malignant. I mean, you see that this is actually benign and this is a malignant cluster. I mean, I don't know how to do it. But the point is, we can't get the doctor to sit with us for all those few thousand images. It's almost impossible. So we try to minimize the labeling and then try to learn from both the labeling and unlabeled data. Okay, so that is basically the idea of semi-supervised learning, as we discussed, right? So this is a few initial things. So you just train 10x data. So basically this, so I had 40x data labeled. This data is mostly unlabeled. So what we can do is, you can just blow this up to 10 times more and try to test it on a model which is trained on this. So that option is there. Okay, so it will give you some idea, but this is inherently having lot of more noise and significantly lower resolution. It won't be a perfect model. So that's what we did. So we tried to build a baseline by training on the 40x data and test on the 4x data. So we got to something like some 0.73 average F score. So you see that this is basically an average of precision and recall. It's around 0.85, and this we didn't care too much because it's anyway benign cells. We were like more worried about these things. So all hyperparameters, everything is tuned for getting this higher. So it was this. So we tried to do those two algorithms, mix match and fix match, as we discussed. So mix match, as you remember, it is about you try to do lot of augmentations. you have the unlabeled image and you do lot of augmentation, change the color, put a noise, shift, rotate, all those things. So you get different predictions and you average them to get a standard prediction which you consider as the pseudo label, and each of these predictions should be same as this by the semi-supervised learning principle. So you try to minimize that mean square error loss. So this is done with that 40x data which we never bothered to label. And with the 10x, 4x, this is a 4x data which is unlabeled. And the 40x data which is labeled, you can train in the usual manner. You have the label, you have the prediction, you minimize the cross entropy. So please, we keep on doing that. And finally, we have some weighting factor between them as the final loss. So the only thing is, so you need to actually worry about labels. Okay, so if you actually have a label here and you do augmentation which is shifting the image, you need to actually shift the label also. So we cannot just average these labels to get to that standard label in the mix match. So what people do is, so what we did is we tried to kind of then, so this is a rotated thing, it will give you a rotated label. You have to do the reverse of it before doing all those averaging. So we tried to do all that. We tried to do reverse augmentation for the labels, then try to come up with align all of them and then centering all those things, and try to do pseudo labeling. So this needed a few more stuff. I mean, you see that we only consider the center part because when you shift and rotate, some of these things are giving very weird outputs. So we try to avoid that. Okay, so these are like, this is just original one, this is shifted one, this is zoomed and cropped part. So you have to reverse the augmentation. So this image is at a different zoom and crop compared to this. So you have to reverse it and align all of them and then average to get the pseudo label. We used all those different augmentations, flipping, zooming and cropping, and height and width shifting, all those with some statistical probability. So every image you take with this probability, you might flip or you might not flip, and similarly. So the training, you don't worry about that. I mean, this is the loss which is the standard cross entropy loss, and this is the loss which is telling those two augmented image and the averaged output should be the same. So again, it's a pixel wise loss because you have a lot of class labels for each pixel. So don't worry too much about that. Okay. So we tried with the different k values and see how we could improve that. So I think here we actually got, so there are different lambda values, these weighting factors. So basically we are trying to optimize for hyperparameters here. And we kind of got to that result. So we had this one shoot up by another 4%, here another 10%. So we kind of made these two models same. So finally, when we got an average value, we had at least a 4% improvement here and another 2% improvement there. So something got better. So this is some results. So if you see, this was the image and okay, have the ground truth here. So there is an image and there is a ground truth there. So here it was all benign, here it was all benign this part, but malignant here. This is benign, this is malignant. But if you look at this, this is actually making everything malignant, these two images. This was actually missing the malignant portion. So this is the mixed match, this is the mobile unit. It was kind of predicting everything as malignant. This was predicting everything as benign. But after you do this averaging, this has improved here. After doing the mixed match, this also has started getting some of the malignancy. Oops. Yeah. So the other thing that we did was the fixed match. The fixed match was basically trying to look at another method, right? So you do a weak augmentation versus strong augmentation. So you have a labeled image, it is the same path as supervised training. You label the image, you predict it, you have the label, you do a cross entropy loss. So unlabeled image, you do weakly augmentation and strong augmentation. This is just either, I think we also shifted and rotated. Basically we didn't we didn't add noise, we didn't keep color transformations, etc. So these were the predictions. This was considered as the pseudo label, and these had other predictions. Okay, and you tried to do a loss there. Sorry, this is not a cross entropy loss, this is a mean square loss. Okay, sorry, it's cross entropy. Okay, I'll check this. I think this was mean square error losses. I've labeled it wrongly. So you have two images. So again we have to kind of reverse all the augmentations before getting into this loss computation. So this is weakly augmented picture and this is a strongly augmented picture, and you try to do this. Of course this is also this is only the fixed match part. You also train it with the supervised data. So this is the kind of augmentations. The normal augmentations, which is flipping and shifting, those are used in the weak augmentation. Change the contrast, change the color, all those zoom and crop, I mean changing the scale here. So this is the range where we change the scale with that probability. So those are all used as the strong augmentation. So this too has to be have this. There will be two outputs from those two, and then we tried to do the loss. Okay. Now there was one extra thing which we did. That is, when the output, you get some probabilities, right? When you give the output, so you get a value saying that whether it is malignant or benign. Only if that probability is high, you try to include it in the training. So you don't include all the regions which are giving you low probabilities from the weak augmentation. So that's an extra thing we had to do, because otherwise it was not converging. So that's one thing we did extra other than the basic paper. Okay, so this is just a formula. So you try to have two different losses. One is supervised, which is standard cross entropy, and then the unsupervised, which is the mean square error. Here I put correctly, and you try to average. Again you try to look at various factors, various kind of weighting. So your unsupervised is kind of 10% weighed as compared to your supervised loss. So you see that it is actually still giving more weightage to the supervised term, but this, with a lot of data, this is able to improve this. So this is the kind of improvements we were seeing. So you had these two baseline models, which is if you only train with supervised data, their performance was less, and here this has improved. If you remember, this was something like 87 before, so this has become 89. This was smaller, and this has become 7% more to become 91, and benign F score was, even that actually improved. So both of these models came up to almost 4 to 5%. This has become 8% better, this has become 4% better. This was originally a better model than that, because this is having all those residual blocks, which actually is a good, better model. This gets trained better than that. Okay, so both of these base models, we were able to improve the average F score, average precision and recall for these tasks. So again, similar set of results. So this is the baseline results. Baseline results are same. Mobile unit was predicting too many malignant regions, and res unit was missing too many malignant regions. But with the fixed match, they were actually getting closer to the ground truth. So here this is, for example, still a misclassification, this region. But between these two, I think it is trying to get close to the ground truth. So that's the fixed match results. So I think this is probably the more important slide. The data is valuable. Whether you have label or not, try to get as much as data as possible. Okay? You may be able to get only few data points labeled, and many times it is not possible to label everything. But still you keep the data. And how do we do SSL? We saw at least 3-4 methods, and depending on your domain you can choose. If you think it's easy to do adversarial training, do adversarial training. If you don't have so much of computation time to generate all adversarial noise, etc., don't worry about it. But at least try to do a mean teacher model or the other data augmentation techniques. Fixed match, mixed match, we found them to be pretty much working at least 2-3 different applications. And one of the crucial thing is here, so you need to have kind of comparable amount of supervised data also. So you should have at least, if you have at least 20% of the data, you should have supervised data. That's the kind of paradigm where it starts working. I mean, if you have like only 1% of data supervised and 99% of data unsupervised, you may not see that much of a performance improvement. Again, you will see that while we trained the loss function, it actually unsupervised loss function got kind of 10% weightage as compared to the supervised thing. So supervised data is important in this framework, but you can still benefit from a lot of unlabeled data. So that's the general idea. Okay. First one now. Any questions? Yeah.
I actually appreciate the kind of work that you do, but I was kind of going through your Google Scholar profile. I couldn't find, there's one actually.
This one?
I couldn't get the page number also of the slide I should have pointed you towards that.
We can go back and see.
Where you authored the paper with someone else, I think 2020 paper, please go back to the...
Yeah, I can tell you the paper, and yeah, I didn't put it here, yeah, sorry.
I saw it actually, but it's not on your Google Scholar profile.
Well, it is in my Google Scholar profile, but try to sort it by year and see if it is around this was 2021, yeah, somewhere around that.
Maybe I skip that. So yeah. How about like, because I kind of tried investigating this, but what it gave me was not at all closer to it. I used the adversarial approach, okay, and it was one of the objectives I framed.
So you actually tried doing
on chest X-ray.
X-ray images?
Yeah, chest X-ray.
Chest X-ray, but this is a classification problem, right?
Yes, yes. So
and did you have labeled data?
So I had quite a few, but
how much?
It was around 300.
300 labels, okay, and unlabeled data?
Yeah, unlabeled is almost 15K.
Okay, and then, okay.
Yes, so...
Okay, it's probably, how good is the supervised data?
So that's what, like, if you have your code, maybe I can look at that and see if I can adapt it.
I'll connect you with somebody. Yeah. Just send me an email. Sure. My email should be there, yeah, in the website, yeah. Okay. Yes, sir.
I have a basic lack of understanding of the deep learning models for general image analysis.
Okay.
For example, in cytology, you train the classifier with cytology examples.
Yes.
For breast cancer, with those examples.
Yes.
Domain specific.
Domain specific. Yes.
You show a video and the cat and so on. In the general scenario outdoors, there could be many possible.
Yeah. Okay.
You have to train with every
No. So this one.
Only for tabby cat or what?
This is only trained with cytology images. Whatever we did, yeah, only with the cytology images. Okay.
And tabby cat is trained only for
No, this is actually trained with, so this is a general vision problem which is famous these days, image classification. So they do what is called as the ImageNet data set. There are around 1,000 different classes of images, and it's a 1 million image data set. And
1,000 types of objects.
1,000 types of objects and 1 million images. Close to, I think slightly.
Open list.
It's, yeah, it can be different things, yeah. So that, okay, I have lot of different data sets in these examples probably. Yeah, this is from the ImageNet classification. There are like lot of different classes. And this is one of the model for that. So you get 1,000 different probability values. And the point is, yeah.
1,000 networks, one for each.
No. Single network which has 1,000 output values. So the point is, yeah, this kind of part is kind of very general because it can distinguish 1,000 different objects. Maybe it can different even other ones also. It kind of extract a relevant feature. So this is one of the model. Then this is another data set. I think it's a data set for, I think it's called Coco or something, MS Coco. This is for a driving data set. So they have a few tens of thousands of, these are actually, there are also another similar data set with videos. So they actually have these pixel level labels for, I think, a few classes which are generally on the road, like buildings, pedestrians, and obstructions, and road, tree, sky, etc.
And what happens when an unknown object comes?
It has to go as an obstruction or something. I think. Obstruction, say a road obstruction or something. I think, of course, it's a data set. It's limited always. What happens with the unknown object, it's still, I mean, we will have to look at it. So this is another data set, and these two are like I took it from outside. And this is, even this is another data set. It was coming in this challenge in ISBI. So it's a ISBI challenge, and it was around 2014, 15, around that time. And this is from Google, and they tried to do some other thing. And this is our data set we collected from doctors.
So essentially the network has to be trained for every kind of object that you want to detect and label.
Yes. I mean even traditionally I think we will have, yeah.
That's a requirement.
Yeah. If we had, I mean even past, right? If you had to train a SCM, we had to train it on AMR, right? Image. People are trying to do something across, but I don't know yet how successful they are. They tried to spool a few things, like that ImageNet, that big data set I was showing, that initial part of that is kind of extracting general features. So they tried to take those weights and try to add with other tasks, but it's only like it's a better initialization. It won't work out of the box, I don't think. Yeah, we.
Just I want to observe a labeling problem per se. Yeah, we have a patch per se.
Yeah.
In that patch, maybe 75% is cat is there. 25% is dog is also there.
So that is this task, no? Semantic segmentation. You kind of label this portion as same problem, right? I mean,
Patch is cat or a dog.
yeah. That's exactly where you have semantic segmentation. I mean, this whole image, is it malignant or benign? We don't know. But this part is definitely malignant cells, and this part is definitely benign cells. It's the same thing, and that's where you need semantic segmentation, right?
Second observation is compared to supervised, when we compare supervised and unsupervised. Supervised is fantastic life.
Yeah, but you don't get to data. You don't get to label. I mean, think about your satellite images. You get the satellite images of.
Unsupervised, we have not yet reached our expectation, like as far as the models are concerned.
Yes. But that's why it is important to look at more things on this, right? I mean, if you are looking at satellite data, it's very difficult to get labeled satellite data. You only have, I don't know, the Italian or US some data, and we have this entire India data which is available but no labels. And yeah, then I think you might know better, probably something in satellite data you have been working.
So there's something that I really need to get clear. See, you said about semantic segmentation, right? But can you go to the previous slide?
Previous slide.
There was a place where we had multiple classes, right?
This is multiple classes,
Okay,
right?
so how about instance-based segmentation then? Because see, my understanding is semantic segmentation is we have a foreground and we have a background. Two classes.
Not necessary. It can be multiple classes, right? I mean,
Yes, sir, yeah.
your driving problem, you have to identify vehicles separately, side separately. Yeah, it is a classification problem.
Yeah. So how do you implement instance-based, right? Then, like, if I
How do you implement what?
instance-based segmentation? Like, see, in a class of car.
Huh.
So I have various models of car.
Okay, instance segmentation. Instance segmentation, okay, people do many things actually. One is, I mean, the simplest thing to do is a connected component analysis here, but not really always useful. I mean, it won't segment these two trees, right? So that instance segmentation is actually a bit tricky, okay, if you ask me. So there are models people propose for doing instance segmentation where you have to kind of have the object in different things and try to kind of get a 2D distribution of the object. I mean, you know that tree is like this, so you try to use that kind of knowledge to train segmentation of the whatever get classified as tree. I mean, you take all these yellow regions and then try to cut it into different trees. Yeah, so you have to train a separate model for that often. Then anything more on instance segmentation?
So, like in pathology data, any image enhancement technique help to improve the performance?
Okay, yeah, that's a good question actually. So there are these two different schools of machine learning training. One is you get the data and you try to make the model robust to noise. So you get all the data, maybe good data, some of them bad data, but in spite of only using good data, you take the data, add some noise, distort it a little bit, and train the system with all kind of inputs, whether it is good or bad. You try to train it with all kind of inputs so that the system is robust to these kind of distortions. So that's one way of doing it. The other way is, as you are telling, enhance the image and try to get it to a very good quality image and then classify. So there are both kind of approaches. So people these days try to do this, making the system more robust, because it's only just a machine learning system. They don't have to think what to do to enhance the signal. Often the enhancing the signal is a more difficult task. Sir, I think you should know. Yeah, you have to do all the signal processing and you have to learn all the distributions of the noise, everything. It's more difficult, but I think, yeah, if you can get to a very good SNR using your enhancement, maybe that's a good way, because your variability is reduced, you don't have noise in your data, so often you will be able to train a simpler machine learning system than very complicated. That's all.
Just a comment on what
Yes, I think, yeah,
It's an interesting observation. In textbooks, when we studied image processing, we studied filtering and enhancement as initial pre-processing steps, thinking that they're easy, and then classification is more difficult.
More
Now
difficult.
you're telling me the reverse. That classification is easier than filtering.
No, it's not easier. Okay, sorry. The point is you need a much more, so you have this complexity of dealing it somewhere. So the point is you deal with some complexity in enhancement and lesser complexity in machine learning, versus you have a huge machine learning system and more complex machine learning system, let it handle everything there. So it's more complex, it's going to have more layers, more computation, more everything.
In addition, there could be noise in the label.
Yeah, That's also there, yeah. So actually a very classical example for this is speech, because I have done some speech research, so I know this. So for at least 50 years, okay, people try to process speech in a particular way. They will take the speech, you know, I mean, you put a mic here and record, right? So you get a waveform, you get a very random kind of waveform. I mean, anybody have seen a speech waveform? It's pretty complicated, okay? There will be a ringing, and then there will be an envelope and all those things. So what people did to process speech is you take smaller intervals to this and try to get the spectrum of it, okay? Spectrum, you know, FFT, right? And then try to find that spectrum in certain bands which are important to hearing, okay? So lower frequencies are more important, so you take more lower spectral bands, and higher frequencies are not so important, so you take wider bands there. You put all these things and then you do a DCT. Don't even ask me why, but it's a way of smoothing out these fine variations in the spectra, okay? And you get some random 20 numbers out of all this processing, and they seems to be very robust in doing this is called Mel frequency Kepstral coefficients, if anybody wants to know. So they seems to be very robust to some of these variations, like I am speaking something, he is speaking something, his voice is totally different, all that signature is there in his speech. This seems to be robust against such variations. And even a different like a gender, I mean, between male and female the speech changes a lot, right? So this seems to be very robust against those things. And people are only using this for like past, not past, I mean few years back, I think around 40 to 50 years people used this without changing. It was just exact the same signal processing which people, and then this was fed to the machine learning model. Now with the deep learning, I think even us back as 2015, 10 years back, people have started to reinvestigate why we should do this. People started learning these filters as part of the network itself. So they put filters here, but the filter coefficients will be learned together with every classifier. But they also found that finally the filters learned are like similar to this, but not exactly these things. So there were the kind. So that's another part. So in your neural network, you can have very special layers. A convolutional layer is nothing but a filter. So you can have a filter which is processing the input, which can often learn from the data. So yeah, that's also there.
When you say that the machine learned filters that are similar to what were designed by human researchers earlier,
yeah.
it's a kind of confirmation.
Yeah, it's good to know.
By a machine later.
Yes, it's good to know, right? Yeah. Well, yeah. True. Huh. Sorry, then I can't hear you. The MFCC here? Uh-huh. Yeah, okay. Few details there. I mean, people are doing not exactly MFCC. There were like different things. Okay. There's a little bit history here. Okay. This MFCCs never worked with a neural network. Okay. That is because they have very different variance across different components. So what worked with neural networks were well filter banks. So it is filter bank, but at a Mel scale, at a smaller scale here and bigger scale here. So they tried to learn the filters. They tried to put a convolutional layer in the first few layers of the neural network and tried to tune their sender frequency and the bandwidth. So it turns out that this happens to have similar structure. They have more sender frequencies here and a smaller bandwidth here and their wider bandwidth. Okay, Raghavendra, I think I am running out of time.
So, I'll thank Professor D2 for his lecture. Now we have a tea break. We will come back at
next slide. Thank you. Good morning. Welcome back. This is my last technical talk. I have one more talk tomorrow, but that will be some general talk about where we go from here further. Most of the images you have seen so far have been grayscale images. Only the retinal fundus images had color, but our processing was using only the Y channel, the luminance channel. So we didn't use the color information. In that case, although it is a full color image, natural color image, the blood vessels have high contrast only in the green channel or the Y or the luminance channel. So only those two channels have been used. Red is noisy, blue is noisy, so they're not used. Just for blood vessel detection. If you want to detect hemorrhages, it may be useful to use the red channel. Now, after writing the two books on biomedical signal analysis and biomedical image analysis, my attention turned to color image processing. By that time, I had worked on a few color image processing projects with my collaborators in Romania, Dr. Mihai and his professor Vasile Buzuloiu, and also in Spain with Begonia Acha and Carmen Serrano. So then we had a few papers, not a whole lot of papers, but we had looked into some aspects of processing or analyzing color images. We had encountered a few applications of color image processing. And also in Brazil, I worked with dermatology images, and there also color is important. So then we said, okay, let's put all these together and see what we can do and to address the basics of color image processing. At that time, when we started working on this book, there were not many textbooks available on color image processing. There were a few compiled books on color image processing with various applications, but most of the books were more on color imaging and color representation, sensors, printers, and such, not on analysis. Some of the classical textbooks on digital image processing had small sections on color image processing, and they have expanded in new editions. But at that time, the color image processing sections in standard digital image processing books were fairly small and did not go into much detail and did not have much in terms of illustrations. Dr. Venetsinopoulos from Toronto, University of Toronto, has a textbook. It's still there, Pitasin Venetsinopoulos, and that's perhaps the first textbook on color image processing. But it lacked illustrations. The fundamentals were there. There were some illustrations, but we wanted to prepare a textbook with more illustrations that could easily and clearly convey some of the notions of color image representation, capture, and add some applications of image processing. At first, we had a big plan, but then we ran out of time and the size of the book and all that. So this is a small book. One of the colleagues of Begonia and Carmen, Jose, is our fourth co-author. We are working on the second edition, which will be expanded compared to the first edition. So again, I would say, don't buy this book. Wait for the next edition, but it may take 2 years. We are working on it. So Begonia Acha and Carmen Serrano are with the University of Sevilla in Spain, and they have visited Calgary many times, and we have worked on various projects, and I have been there a few times. So this is a collaborative project between the University of Calgary and the Universidad de Sevilla in Spain. Now that's the cover of our book, showing retinal fundus images, the original color image and its red, green, and blue components, and the color circle that I'll explain as we go along. So first, let's look at the nature of color image process, color images. What are color images? What is color? And how do we represent? Where do we encounter color? Where is it important? In Canada, sometimes we get double rainbows, even triple rainbows I have seen. And interestingly, the second rainbow has the colors in the reverse order. And then I have seen multiple such patterns. I got this from Chris Pollock, who is a famous photographer, in the Kananaskis Mountains, very close to Calgary. 75 kilometers from Calgary, we have a beautiful provincial park where we go for hiking. So the color spectrum is this, where out of the total spectrum that we get from the sun, there is a very small portion, 380 to 750 nanometers, that our visual system can perceive. And some people may not be sensitive to certain parts of the spectrum. They may have different sensitivity or limited sensitivity. Some animals may have a bit more into these ranges, beyond the red and into UV. So it depends upon the biological system, and there could be some variations between people in the sensitivity and reception of this range. But it's a very narrow range compared to the total range, going from low frequency radio waves to very high frequency, going beyond ultraviolet into cosmic rays. We're not sensitive to those. What are the important color attributes? The most important is hue, that is the dominant wavelength or band in the spectrum. So we're not talking about one frequency, but a band. Saturation, what is the quality or colorfulness of that color? Is that pure red, or is it diluted with white, sort of rose pink and light pink and so on? Intensity of brightness, but that is not color. So these are the chromatic components, or chrominance components, and this is just the non-chromatic, or just the intensity part. So intensity brightness, that is what we call grayscale. I don't know why it is called grayscale. It should be a brightness scale. Gray means dark. So 255 in gray should be dark, but it's reversed. Chroma and lightness and a few other terms are used in the literature, but these are perhaps most commonly used. So the HSI system, or HSV sometimes is called value. HSI is perhaps the most common representation, where hue and saturation represent the actual color components, and intensity is just the brightness part, no color. The human visual system has rods that are sensitive to light intensity only. And so we can see in a dark room also, but we don't perceive color. If we turn off all the lights, not turn off all the lights, but keep a little bit of light, we can still see you, but we won't be able to differentiate between colors. So the cones that are sensitive to light work at a slightly higher light level. We need some minimum amount of light for the cones to work, and they are sensitive to red, green, and blue. Not just RGB, but bands like this. So they're called long, medium, and short cones, LMS, L commonly done. And then CMYK, cyan, magenta, yellow, and black, for printing purposes. Now black is added only to minimize the use of all these colors. If you combine CMY, you get black, but why throw that much ink? You're wasting ink to get black, so black is added. You could add white here if you want and call it RGBW, but that is not commonly done. This is for light, and this is for dyes in printing. So this could be called the additive primaries, and this could be called the subtractive primaries or secondary primaries. HSI, as I mentioned, and then there are some standardized representations from the International Commission for Light. CIE is the French name for the International Commission for Light, and some committees have come up with standardized representations to improve the representation of color and bring certain measures of color closer to human visual perception, such that some attributes and distance measures computed in these domains match or agree with human visual perception. RGB may not agree with human perception when you compute measures and differences. And then there are these others, YIQ, YUV, and so on, that have been used for various other representations of color signals in TV and other applications. CIE also came up with standardized RGB in XYZ coordinates. I'll mention some of them. not all of them. So here we have what are called color matching functions. Given an arbitrary color, can you represent that in terms of coordinates in some space? Like using basis functions. We have seen wavelets, Fourier transforms. So here we have color matching functions defined in the wavelength spectral domain. Wavelength, or take the inverse, you get frequency. So this is essentially the spectrum related to red, green, and blue, but these are what are called color matching functions. So when you take the projection of a given arbitrary color spectrum that has a combination of RGB, you project onto this, you get the blue component, and project to that green, project to that red, but then the red has been defined with some negative values. Of course, there is no negative light, but that function has been defined with negative values. And that has been changed in this to be all positive. So these are color matching functions in the XYZ domain. So now you take the projections onto these XYZ functions, spectral functions. Take projections of the spectrum of your color signal. And then you get the XYZ components, like the Fourier coefficients or DCT, whatever. Okay? Projection is the dot product or point by point product and addition of your spectrum with one of these. You get the corresponding component. Then you represent the arbitrary color in terms of these XYZ coordinates, and if you normalize by dividing by x plus y plus z, then z is 1 minus x minus y. You only need 2. You don't need 3 after normalization. So there is this CIE, so Commission Internationale d'Éclairage is that CIE, International Commission for Light. So this is a domain or a space that is defined with red, orange, yellow, green, cyan, blue, violet. And this could be the gamut of some device or sensor. Not all devices and sensors and visual systems may occupy this whole range. So this is of somebody, something. And there is a reference light given D65. Some illumination source is specified. So this is the XY plane. X coordinate, Y coordinate, with projections with respect to those functions, like the color matching functions, normalized by x plus y plus z. So z is not required because it is 1 minus x minus y. So now the 3D variable is displayed on a 2D grid, if you want to call it, or space. And within this range, you can display or show the gamuts or the operating range of different devices and systems. So you can give the coordinates of a color representation in this manner using RGB that are mutually orthogonal in some sense, or cyan, magenta, yellow, and black is at the origin, white is there. So you have this color cube now. So an arbitrary color will be a point somewhere inside, depending upon which system you use. And RGB and CMY are complementary in this sense. Now it is better perhaps to represent using the dual cone model here, where HSI values are used. Here, intensity is this vertical axis, going black to white. When there is no light, you can't see color. So no point in showing this. You could also show this as a cylinder if you want. But we don't perceive color here. Similarly, when there is the highest amount of light, we don't perceive color. So color exists or is perceived somewhere in the middle for a certain range, and on both sides, color perception vanishes. So that is intensity. Hue is the angle in the circle. Saturation is the radial distance within that circle. So hue typically is represented with red at 0, yellow, green, cyan, blue, magenta. And then A point here will be red, but not pure red. If you want pure red, you are there on the circle. If you come closer to 0, the center of this axis, then red becomes lower and lower shades of pink, lighter and lighter shades of pink. Similarly, green and other things. Okay, so this is HSI. So to show in pictures, I like to show these as pictures. So I spent some time in MATLAB playing around, and I was happy when some nice pictures came out. Some of these are obvious, but until they are shown, they are not obvious perhaps. So if varying hue with constant saturation and intensity, so there is no saturation variable here, so the same color comes right through, but the color is red here and slowly moving towards yellow and green and cyan, blue and magenta, and then merging back to red. So it is periodic if you want to go around. So you only go 0 to 360 for 360, not 180 for hue. And there are these diametrically opposite colors. So this is a vector space. So if you have a red vector and a cyan vector and add them, you get 0, right? So that way, and the separation red to green is 120 degrees, green to blue is 120, blue back to red is 120. And cyan, magenta, yellow are similarly placed. Now if you include saturation variability, then from here, as you go to that is pure red and various shades of pink, and the color gets lighter and lighter as you come close to the origin. So this axis is saturation axis. Okay. So that is Begonia and that is Carmen, and we have worked together for a few years, more than 20 years. So we said, well, let's have some fun and got RGB, and that's the red component. Where you have red, the values are high. Blue have nothing, so my blue component is 0, and for her the green component is, and so on. Right? Obvious. So this is red plus green plus blue. So if you add them together, you will get that. Now how do you represent this information of a digital image? We take the histogram of a grayscale image of the number of counts of each gray level. Now we have multiple possibilities: red, green, blue, intensity, and so on. So the black line is grayscale, red is the red histogram, there is a large peak, that is my shirt, and there are some low values of red. Sevilla is very hot in the summer, hot and dry, 45 degrees, you can't even touch the car door handles, 45 and more. And the streets in the downtown area are very narrow. That's the way they designed it in the olden days, so to prevent attackers from coming in with big vehicles or large numbers. But everybody has the AC unit facing that way, so you cannot even walk in these narrow corridors because all the AC units are blasting hot air out. It's already hot. So we got a little roasted, I suppose. So there is some red there too, and that wall there has a combination. So there are some low levels of red that are not so obvious, and the others green and blue. So that's one of the blue shirts, that's one of the green tops, I suppose. We can also plot in 3D. Shantanu Bonik, my PhD student, developed this program. I had seen this in some of the books. So it's a 3D plot of the occurrence of various colors in the RGB cube. So the intensity of this represents, the value of that represents how many pixels have that value of red or that, and so on. So the yellow part is here, the red is somewhere here, the green, all that is there, the cyan or blue, it's there, and so on. You can perform 3D segmentation in this space. HSI, if you compute the hue angle and saturation and intensity, these are the components. But there is a problem with hue, for red especially. You get red here, 0, degrees. 1 degree is red, but 360, 359 is also red. So if it jumps between 0, 1, and 359, you are jumping across a large range. So the red here, my shirt, has all these very bright values for 359 degrees and very low values for 0, 1 degree, and so on. That's a discontinuity in the representation of hue. For the other blue and green, it's not a problem. Okay, saturation, my shirt is pure red. That is not pure green. That blue perhaps is close to pure blue. If you take the sine of hue divided by 2, then that becomes distance from red. So don't display the angle as such, take the sine, and then those things are cleaned up. So what is the distance from red? So positive or negative? 1 degree this way or 1 degree that way is the same distance from red. And you can then display sine of hue over 2. Sine of hue of 120 divided by 2 is distance from green. So this is green, so the distance is 0. And red and blue are equidistant from green. So these two regions have the same distance. So you can take a distance measure and then analyze color with reference to some color. Then you can overcome some of these limitations of representation of hue in angle. So if you want only the color information, the chrominance component, take the luminance away, then in the HSI system, you want just hue and saturation. So there are only 2 variables for color. So now you can plot the histogram within this ring, going from red and so on, I mentioned earlier. So my red shirt is there with high saturation. And that perhaps is the wall, sort of between yellow and some sort of brown. And, or maybe this, sorry. Now this would be that wall. And the green top is there and the blue top is here. So now we can perform segmentation of color only, throw the intensity out in 2D, in a 2D space. So if you play around with hue, saturation, and intensity, you can get a few different types of pictures. Here I have kept the hue component with maximum saturation and intensity. So this green is not the real green. Green is that. Sometimes I get confused. No, that looks green. No, but green is that. Similarly, blue is that. There. Maximum saturation. Whatever that color is, saturated rather. This is iso intensity rendition with original hue and saturation. The intensity is maximum. And the original values of the saturation, yeah. And the last one is just the intensity component, grayscale. So in this way you can extract different types of images depending upon which part is of interest, intensity, hue, saturation. And then you can separate chromatic and achromatic or non-chromatic pixels. In this image, which pixels have no color? Nearly black, nearly white. So close to the saturation being 0, go there and take those pixels. Put a condition that regardless of the hue angle, saturation must be less than something. Whatever cutoff, 0.1, 0.2, something. And then if the intensity is also below a certain threshold, you get black pixels. If the intensity is above some threshold, you get the white pixels. There's a little bit of color, so the saturation is not 0. I allowed up to 0.1 or I don't have that number, some threshold. If I put all of them together, I get the non-chromatic pixels, pixels with almost no color. Then there is the question about natural versus pseudo color. So I put a number of pictures, took a number of pictures. The machine lab in our department, RGB used there. Here RYK, no, Y is used in India for one of the phases. There it is RGB, and depends on the country. That color code, there is black here for ground, and so on. So you use that just to connect properly the phases. That's just convention. So that is color coding. And this is for artistic representation. The color represents the nature of that character in the play, and just to make it more attractive. In pathology, stains are applied. The color is not a natural color. It depends upon the stain that you put and how many stains and how they interact. And certain parts of the tissue will take up certain stains, others will take other stains. So they get colored differently, but that is not natural color. You can call it color coding or pseudo-coloring, both. But perhaps more accurately it is color coding, because the color tells the pathologist what that represents. There is a code there. Or some toys for visual matching of objects for babies and children to learn about color. Retinal image, this is natural. The palettes, that is natural. In retinal images also, color can play important roles when there are exudates that are bright, not necessarily always white, yellowish. And there could be some greenish pigment deposits. Red represents hemorrhage, and blood vessels are here. The optic nerve head area is also typically bright. Yellow, not really white. Sort of yellow to white. So color has some meaning here. In the normal case, color doesn't play an important role. Although we see the blood vessels as being sort of red, the contrast between the vessels and the background, which is also sort of reddish, is the best in the green channel, not the red channel. And there is no blue in most of our body, unless you get hit and there is a bruise that could appear to be blue. But there is some green in somehow, in some places. Just a pigment. Maybe that's some combination. In medical imaging, when you fuse multimodal medical images, in this case MR and PET, I think, you have one image here that is MR, this is PET showing some increased activity there, and when you fuse, you can include the anatomical information with the physiological information or functional. This is purely anatomy. This shows the anatomy, but not in high resolution, but it shows the uptake of some radiopharmaceutical that is put into the patient, injected to the patient. So this is functional imaging. So it depends upon how that part of the body is functioning. If there is a tumor, it takes more blood supply, hence it's of a higher intensity. Put them together, you can interpret this functional image in the context of the anatomy. And their color is important. Even here, this is pseudo color, it doesn't matter. You can show it in any color you want, but it was given red color, and you put them together, this shows up in red on top of the grayscale image. You could put it in green if you like. So it doesn't matter, but it is pseudo coloring. In early days of computer tomography, because of the large dynamic range of -1000 to 1000, to display on ordinary CT, ordinary computer monitors, which used to be video devices at that time, it was felt that, or some recommended that, well, why don't you go to color? Because the human visual system at a given level of adaptation to light and how much your pupil has opened, you can perceive perhaps a few tens of gray levels, maybe 20, 30 gray levels, that's all. But we can adapt. We can window. I can see details here at various light levels, but I have to wait for my people to adjust to that lighting. And we can go outside, I can still perceive you as you. So what matters is the difference. As I mentioned, the human visual system is a bandpass system. The absolute intensity doesn't matter. I can see you with a little bit light and recognize you, and also out in the sunlight. But we can perceive more shades of color, hue, saturation, and so on, with intensity. So it was felt in the early days of CT imaging that because of the large dynamic range of CT images, it would be better to map them to some color. But it's only one value per pixel. So turn one value to 3 values of RGB, you get some fancy colors, and yeah, you can see some details, but they are totally out in the sense it doesn't look like the original CT image. So those methods of pseudo coloring failed. Radiologists were not impressed. Computer scientists perhaps thought it was cool, but radiologists did not really catch on to that. They were happy with just shifting the window of the Hounsfield unit values and looking at low density tissue, soft tissue, hard tissue, bone, and so on separately. So it is important to recognize here that our system can recognize and distinguish between only a few tenths of gray levels right now, for me, in this setting. Turn down the light level, and my pupil will open up a little bit more. Then I can see all of you again in a very similar manner, but we have shifted in the range of the grayscale. But it takes some adaptation. And again, as I said, we go outside, bright light, we can see. But if you come from bright light suddenly to low light level, we are sort of blinded for a little while. We can't see anything. Similarly, after adaptation to this, you suddenly go outside, you can't see anything. And it takes a little while for this change to occur. Whereas color, we can see more. But color can be seen only when there is adequate light. Acquisition of color images. A sensor with color filter array data. So we don't have separate sensors for RGB in most cases. An intensity detector is used with a filter to capture in one shot. If you want, you can have different sensors for RGB, but then it takes time. And we won't stay still, we will move, and the picture is ruined. So one sensor of light, put filters. You can put 3 filters and take RGB separately, but that takes time too. So instead, there is a color filter array. You need dark current correction because the CCD elements have some noise. So even when there is no light, when the lens cap is on, there will be some electrons jumping around due to thermal energy, and there will be some dark current you have to correct for that. Quite balanced. The color we perceive depends upon the spectrum of the light. There could be some bluish tinge here. If I stand here, I don't have any color, so it doesn't matter. But those of you who have gone shopping for clothing material, especially saris, know that the color of the material, the sari, let's say, I like sari shopping too. We went sari shopping, but the color changes with the light, whether it is fluorescent light or it used to be incandescent, but nowadays LED could give you anything. Previously, LEDs only gave one particular band of light. Nowadays, they give you a different spectrum. And that light will affect the way you perceive. The spectrum of the light is reflected from the object, and if the spectrum is not uniform, what you perceive is not the true color. The same we saw with any projection. The received image is the product of the reflectivity of the object with the illuminating function, light. If the light is not uniform, you're not getting my picture, it is some distorted picture. Similarly for color, the spectrum of color. So it is common, I don't know if you still do it, look at the sari in the light in the shop and then say, well, I want to check the color outside. Come outside, check in sunlight, and then in Bangalore, the sales person, many of them are men there, so they would even wrap the sari around them and show with pleating and everything. And then you tell the guy, well, this is fluorescent light, come outside, I want to see you in sunlight. So the guy with the sari has to go outside too. Anyway, that is white balance. You have to correct for that. Demosaicing, I'll show you that. The mosaic of the color filter array. Color transformation to unrendered color space and color transformation to rendered color space. So demosaicing is interpolation to get the other color components from a single pixel of the received array, which will have only one color component because of the filter that is put on your CCD detector. The CCD detector just detects intensity. There is a filter on top with RGB. So under element 3, you only get the CCD under that will give you the red component, that will give you the green, and those will give you blue. So to get the other components, to get the green and blue components for number 3, then there are some demosaicing algorithms that say, this is one of them, that says get the horizontal gradient, delta H is G2 minus G4. Get the vertical G1 minus G5. And if delta H is more than delta V, you come here and average these, G1 plus G5 over 2. And G3, that goes to number 3. And if delta H is less than delta V, average 2 and 4. So G3 gets G2 plus G4. Otherwise, you average all 4. Green. The blue will be in the corners. And do the same for the blue. So instead of just averaging all the 4 green, all the 4 blue data in the neighboring pixels in the 3 by 3 block, you take combinations of 2 or 4 depending upon the vertical or horizontal gradient. So you don't blur across edges. That's the idea. So this pixel will only get the red value from the original sensor data. The blue and green components for that are estimated in this manner. And the same for the others. So these are some of these charts that have been prepared, or this is one of the charts prepared, called the Macbeth color checker. And when you image this using different light sources, you get different colors. So the colors are the same. It's a printed piece of something on paper or some material. And that's like a test pattern, let's say a phantom image. And the values, the RGB values for each of those patches is given by the manufacturer, standard, in XYZ or RGB. So this is using what is called a xenon flash. This is fluorescent light. This is diffuse sunlight. So much difference, and that's why you want this array out in the sunlight, assuming that to be the true color. So there is substantial variation. So you have to correct for that. If you have this color checker, then you say, okay, this is supposed to be that color, but I'm getting that color, so do some correction for that. So that is color calibration. Oh, I'm supposed to give you an image alert, and some said, well, don't show me these pictures without telling me first. If you don't like it, close your eyes. So Begonia and Carmen worked on teledermatology, where in some primary healthcare center, if a person has some sort of a lesion, in this case due to burn, it has to be diagnosed immediately and some treatment has to be applied immediately, but specialists are always in cities, radiologists, dermatologists, whatever. So you need to send those pictures by some sort of data transmission. But then the calibration of the color is important. So here, this was taken with a xenon flash using Canon camera, B's Sony camera. Now, there is a difference in the magnification, but the colors are slightly different. There is a bit of a magenta here, which is not there. After calibration, what is called characterization, these are the images where they are almost the same in color, except for the scale. The color difference here has been reduced. So you could say this is the correct color. Filtering you have seen. So let me talk about some filters for color images. Neighborhood shapes you have seen. Mean and median filter you have seen. So we'll just skip all of that. Now, in the case of scalar pixel values, each pixel has one value. So doing this is easy. In the case of vectors, taking the mean is not a problem. You can add vectors. These are the RGB pixel values in a 3 by 3 neighborhood of a color image, actual values. In all my examples, I like to have actual values. I can make up some numbers, but I try to give real data. So these are real pixels extracted from some image. This is the center pixel and the 3 by 3 neighborhood. So each pixel now has 3 values, RGB or whatever else you have converted it to. RGB you can average easily, just R plus, add all the R components, divide by 9 and so on. So that is not a problem. But median is a problem. How do you sort a vector with 3 components? Because you want to get the median, which is the middle of that ordered list from minimum to maximum. So marginal median was suggested initially. They said, well, take one of the components and sort by that, red only. And take the green and sort, and take the blue and sort. But now these, if you do that, these colors did not exist in the original image. You get some other color. Take the median and it is something, some value of that. This is called marginal, but then you are creating a new color. All these are values that did not exist in the original image. Perhaps some existed somewhere else, who knows. Reduced ordering says, compute some measure rather than the actual pixel values. Use something as a reference and compare each of these pixels in that neighborhood with that reference. Compute a distance. The simplest is Euclidean distance to the mean. X bar is a mean of those 9 pixels. And take xi minus x bar, transpose xi minus x bar, or component-wise difference square and add over all the components. And these are the distances. Now you rank order by distance to the mean. Now this quantity is a scalar. Rank ordering is not a problem. So you are not rank ordering the actual RGB values directly, but instead you are computing some function with reference to something. And here it is Euclidean distance. So some will say, well, Euclidean distance in RGB is not good. So okay, go to LUV, LAB, whatever you like, and do that. Okay, so that is the mean value, mean of all these RGB values. Take the distance, and these are the distances truncated to just integers, rank order. Now, here you don't go to the middle, you take the first one, that is the closest to the mean. You take that. Now there are other distances, vector median and vector directional. The sum of distances from each vector to all other vectors, di. And then this d is Euclidean distance from xi to xk. And that the sum of all that. So how far are all these pixels in the neighborhood separated? Use that as a reference. And take the one closest to that. That has a minimum distance, rather. The distance could also be in terms of angle, color, throw intensity out, and take the angle, which is given by the dot product normalized and cosine inverse. So for each pixel in the neighborhood, you compute the angle. So different measures to convert the three-dimensional vector to a scalar and use that information to make your decision as to how you want to rank order and which one you want to select for the output. So there are a number of these filters in the literature from the Toronto group, Dr. Venetsinopoulos group, and many others, modified and so on. So we took our adaptive neighborhood method that I described earlier. For every pixel, we grow a region, adaptive region of any size and shape, depending upon what is present at that location. So we get a certain population of pixels belonging to the same object without crossing boundaries. We don't want to blur across boundaries of objects. How many pixels do you want? You may put a limit. You may say 50 pixels will be enough because I'm just averaging them, or 100, or how many ever. But now the region is adaptive, like this. So this is an edge in an actual image. I don't remember which one. That is the seed pixel. From that seed pixel, sorry, this is a noisy image, a lot of noise. That became this due to noise. And that is the initial region grown. There are a number of pixels within the region that were not captured because of the region growing criteria. Mihai Chuk said, well, we should include some of them because we don't want only those pixels that are exactly similar to the seed. For averaging, we need a certain population of pixels around that in this space. So then you check for these connected pixels that are within the region and put some additional condition and include them, and the white region now is the adaptive region. There are still a few pixels that are not included because they differ by substantial amounts compared to the seed. So that is the region, and when you average this, you get a clean pixel value, and when you do that for this image, that is the output. So the effect of noise, you see all these other colors, has been suppressed. The edge has not been blurred substantially. This is zoomed into a small region. I think it's this Pepper's image. So we have many different filtered versions. I would ask you to look at these images and judge which one is the best. We have, in our papers, we have the tables of various measures. I won't go into all of those details. We did this with various types of noise. This is with Gaussian additive noise. These two are the same. There are two different images in the book. But this is, C is the MMF, the mean filter, and vector median, and distance, DDF, GVDF, and so on. And ours is where? Ours is the last, of course, and this is the adaptive neighborhood filter. So you could compare this. There are so many other filters. I have not gone into those details. This is just a very broad overview, like an introduction to color image processing. So I'm not going to describe all of these other modified distance filters. We have described them in the book and also in this paper in SPIE, Journal of Digital Imaging, Journal of Electronic Imaging. So we showed that our approach gave the best result compared to these other pictures, other filters, in terms of some distance measures. But again, distance measures are, all distance measures don't correlate well with the human visual perception of what is good and what is bad in terms of noise, sharpness, and such. Enhancement of color images. One needs to be careful. Sometimes component-wise enhancement and filtering will work, sometimes it doesn't work. So if you just do what we have done for grayscale on RGB separately, sometimes it may give you good result. If you are happy, fine. Sometimes it messes up color, especially. Quite often the enhancement that is required, I'm not talking about noise removal, but contrast enhancement. Quite often it is only for the intensity component. You don't want to touch color. You will assume that the color sensor has done its job. If not, do the color calibration using that color checker. For that, you must take a picture of that first and keep it for the same lighting condition. And do the color correction separately. Noise, do the noise filtering, one of those methods. Preferably using the color angle information also. For contrast enhancement, only the intensity component needs to be modified in most cases. Keep the hue and saturation the same. If you want to adjust saturation, do it separately. If you want to make the color more lively or brighter, but it will be unnatural sometimes. So gamma correction, histogram equalization, there are two methods we have seen, can be applied to the intensity component. Saturation may need to be increased if you want it to be more lively and more sometimes glaring. You normally don't alter the hue component unless you want to do something very specific. Not typically, perhaps not for natural images. RGB separate analysis is not usually recommended. So gamma correction, I took this picture in Brazil. It doesn't matter where. There is the restaurant there, and a nice mango tree here with the fruit hanging there. But I took it this way, and there is so much background light. The mangoes here don't show up in the natural color. They're almost black because there is no light going this way. So we want to enhance the color here and perhaps the contrast. And gamma correction applied to intensity only with gamma equal to 0.4. This is enough. The color, you can see the mangoes, they just intensity correction. Oh, you can see the green here. The rest of the color, they are natural colors. I didn't touch color. Okay. See, intensity and saturation enhanced with gamma equal to 0.4. Green is green, okay, but that color is different. The grass is, I don't think you have grass in fluorescent green like that. So that is unnatural color. All the three RGB components enhanced individually with gamma equal to 0.4, not bad. You can see some of the details inside this restaurant that you cannot see there. And also here you can see some if you zoom in, because that's dark compared to the outside sky. And also look at the sky color. You may see sky like that sometimes, but that's not what it was there. That perhaps is the true color of the sky there. This is not bad, but that should be the best using the considerations we have discussed. To enhance contrast, we can use a definition of contrast like this: PR minus PN over PN, like F minus B over B. We have seen the region of interest and its background, and that is grayscale contrast. Or you can use this, PR minus PN over PR plus PN. You can use a circular region. You can use 3 by 3. You can say, this is my region of interest. My reference is somewhere else in the image. Something. You need some reference for the denominator. Grayscale is not a problem. How do you define color contrast? Well, first, the luminance contrast is LMN minus LM over delta L max. I'll give the reference to this paper. This is not our method. So luminance, the color difference was computed in the LAB space, or L star, A star, B star. I just say LAB. So take the Euclidean distance between the two values, foreground, background. The average, the foreground, average of the background, the L1 and L2, A1, A2, B1, B2. So you're taking the same Euclidean distance, but now in the LAB space, and that is supposed to be closer to the human visual perception in terms of differentiating between colors. And then CC, color contrast, is CDM over CD max over the entire image. M is the mean over 5 by 5 region. So this is color contrast. Just Euclidean distance. And then the enhancement is defined in terms of a certain gain for the luminance and a certain gain for the color for every pixel. And that luminance gain is given in terms of these quantities, delta CMN, which is this difference CLCC described earlier. So K is this ratio of LE to L, and the red component is multiplied with KMN, and the same for green and blue. So eventually the multiplication of this factor is done separately, channel by channel, RGB. But they are computed using both color and luminance contrast. So both are enhanced using all of these differences and gradient measures computed, and contrast measures, simultaneous contrast measures. You can call this also simultaneous because you're comparing two values. So this was based on a paper by Liu and Yan. I implemented that and got quite good results. I took this picture of a pagoda in Japan, and because I was taking a picture this way and the sunlight is coming from above, the details here are not seen. There's no light going this way. So that's the luminance contrast, and this is the color contrast. So color contrast exists in pixels other than luminance contrast. There is color contrast here. That's a different color. Not so much there. And this is after enhancement. Of course, you can enhance what is there. If it is not there in the original, if it is black, it will be black. So that's the original. You can see some things there. Something has to be there. You can't just create it by magic. But now it is much better. All the color comes up. Okay? Mihai Ciuc from Romania, with Professor Buzuloiu, we did this work and published this many years ago, 25 years ago, in the Journal of Electronic Imaging. Color histogram equalization, there are a few different methods. The histogram of a color image is a 3D entity. And based on that, some have said equalize in 3D, equalize RGB separately, and there are many other algorithms. And we wanted to try our adaptive neighborhood paradigm for everything. As I said, when you have a hammer, all problems look like a nail, you want to bang it. But there is some reasoning, as I said. Here we said, okay, we don't want to blow up all colors over the entire gamut. That ruins things. And in most cases, only intensity is to be modified. Color we keep. We will assume that the colors are good, have been captured properly. We don't want to create artificial colors or colors that don't exist in the original. So we brought our adaptive neighborhood histogram equalization technique, put some more conditions to make that method work better with color images. So here is a picture from one of the, again, there are some databases and journals expect you to show your results with all of them. For color printing, it was expensive. They wanted $1,000 per page of color, $1,000. And we had 10 pages. And they said, well, put 5 more test images. We said, well, who's going to pay for that? But anyway, we did that, and I had to go and ask the president's office, go with a begging bowl and ask for money, which they gave me. So this is the original image, and what histogram equalization of each RGB separately. This mountain has become purple, and the green is okay. That part is okay, but this purple perhaps doesn't exist. And some colors here are not present in the original. C is 3D histogram equalization, not so good. Histogram decimation is another technique. All these magenta color pixels have come up. E is histogram explosion. Again, other colors have popped up. This is our technique with some parameters for the number of pixels and some other region growing parameters. So we made some measures and said, well, we're not introducing any other color. Has contrast improved? So we showed some measures, and the main thing was not to bring in other arbitrary colors. Segmentation of color images. As I mentioned earlier, we have the 3D histogram in RGB, and you can define a block. So much of R, so much of G, so much of B, but it's very difficult. I cannot conceptualize or visualize how much of green and red and blue I should put to get this color or that color. Perhaps some of you can do that. But it will be perhaps easier in this plane, hue and saturation, right? And by looking at this, we know where various colors lie. I cannot visualize it here. Perhaps with experience, looking at the 3D histogram I showed for the parrot and others, you can do that. And artists do that. They simply take this color and this color, and mix it, and they do that. So it depends upon your experience and how you can imagine these colors. But to me, I can say yellows are there and brown is there and red and pink are here, green. It's easier, more intuitive. So put a limit on saturation, which is the radius, and put a limit on the hue, which is the angular range, like a sector filter. We have seen sector filters in the frequency domain for directional filtering. Now direction relates to hue. So segmented green and cyan and yellow. I gave the same range for all of them. And yellow included some of these greens that are, I gave perhaps too broad a range for each one of them. I think I gave 30 degrees. Yellow doesn't span 30 degrees. It's a very narrow range, yellow. So I could have used 10 degrees and perhaps I would have had only yellow and not those. And last one is black. There is some black there. I can get the white also. I showed earlier how to get the non-chromatic or achromatic parts of the image. So image segmentation into colored parts can be done this way. Now depending on the threshold you put on saturation, you may get only the pure saturated colors or lighter shades of that color too. So this is the sector filter. If you go all the way down here, you will get all the colors of different saturation in that band. You can make the band as narrow or as wide as you want it to be. So another image alert. If you don't like this image, look the other way. Oh, red there. So this is an image of a skin ulcer in collaboration with Dr. Paulo Mazzoncini in Brazil and his colleagues, a dermatologist. Diabetes causes certain problems and the veins don't work properly in the leg and blood circulation is impeded by venous deficiency. Or there are some different names for that. And then blood circulation is affected and wounds don't heal, and ulcers could be caused by this stagnant blood, and there could be lesions of this kind. They're treated, of course, and the response to treatment is what is important. You want to know what is the tissue composition, like we saw the Gaussian mixture modeling of breast tissue or neuroblastoma tumors. So what is the composition of this and how is it changing with respect to treatment? So even the initial treatment depends upon the composition. So here, the 3D histogram is shown here. Now, there are some standard protocols. There is the blue sheet always in the background, and there is a color calibration strip. I don't know why they put it on the patient's foot. It could have been kept somewhere else, but anyway, that's what they did. And here you have the pure RGB and CMYK patches, so you can calibrate the image. We didn't do the calibration, but it is possible. This is like those color checker big matrix I showed. This is something like that. So this is the color histogram, including the blue background and everything. Hue saturation histogram. Red is here, yellow is there, and so on. And blue is, there is a large number of pixels here from the background cloth. So segmentation of red, what is called the granulation tissue, saturation more than 0.4 and hue 300 degrees to 0 to 30 degrees. So we put a 60-degree band there, and that's what we get. Now there are some parts here that are passed because saturation is 0.4. This is not red, it is sort of brown, but it has some red. If I had used a different saturation level, perhaps that wouldn't have come up, but then it is possible then to lose some of the lesion part. Yellow is called fibrin. I went with a lower saturation, 0.2, 30 to 90 degrees. It could be made narrower. Yellow doesn't go that far. But that is, the yellow patch also has come. The red and pink patches are here from this calibration patch. Black is necrotic scar. There isn't much, maybe only that little bit. So the model used here in the analysis of skin ulcers is what is called RYK. So how much is red, how much is yellow, how much is black? Black is scar, means it is healing. Yellow is not good. You want red and black. So depending on how much yellow is there, the treatment could be different, how much red is there. And you could follow treatment, the response of the lesion to treatment. So then you can label this as the ulcer region by putting these three components together. How big is the ulcer? Get the area, relative area of red and yellow and black. Okay, so it's not Gaussian mixture, it's actually pixel by pixel. We didn't plot the distribution and so on. We did a little bit of investigation of this and then passed it to the group of the dermatologists, and they did some more work later, and we also computed color texture. Gray level co-occurrence, in the gray level range, you count how many times 0, 0, 0, 1, 0, 2 have occurred, and 1, 1, 1, 2 and all that. You saw the gray level co-occurrence matrix. Now you can do red, red, blue, blue, green, green, like gray level, and then you can do red, green, green, blue, blue, red. You can do all of those. If you want, you can do RGB co-occurrence, but you may not get that many counts of RGB. So it may be better to do RR, GG, BB, and then RG, GB, RB, and that should be enough. And then you can compute all those statistics of Haralick and others. And we have done some work on that. I won't go into that now. So segmentation, just a few more minutes, 7 more pages, I think. I thought I had 53. How many do I have? 53. I'm almost there at the end. Segmentation, the K-means algorithm is a pattern classification algorithm that can be used for color segmentation too. We have a color feature vector here for each pixel, RGB or LAB, whatever. Whichever color coordinate system you use, it's a vector. So you want to ask, does this pixel belong to this category or this color reference, whatever the reference prototype is. So we have a pixel data set x1, x2, each one of them a vector in R3. Now I'm talking of like our colleagues, R3, R2 and all that. I usually don't use this, I say in the 3D space of RGB, but in the R3 space, V is a code book of centroids for the how many ever regions you want the output to be, to represent. V1 to Vk. And this is a set of pixels corresponding to Vi, x belonging to this capital X, such that the argument of this is given minimum of x minus Vj square. That is, compare each one to each one of these and take the minimum. And that is the class. So starting from a finite data set X, iteratively move the K code vector so as to minimize an error measure and recalculate the sets. That is, you have said you have so many, you want so many classes, and you started with some initialization of the means of those, the centroids of those, some arbitrary values, or you can select some of the RGB values from the image and say initialize to those. There is the error, x minus Vi modulus, and summed over all the categories and all the pixels belonging to those categories, and compute the new centroid, or K means the mean of that category, the ith category, and then keep iterating until there is no more change in the assignment of pixels to categories, or the centroids don't move anymore. So here we have an original image with lots of colors, and the results of K-means clustering in 3 different color spaces: sRGB, S is the standardized RGB, this is HSV, similar to HSI. The intensity and values, the name itself is value. Okay, the intensity I component and V component are obtained in using different combinations of RGB. So HSI and HSV are similar, but the third component, intensity component, is computed differently, and LAB. The image has been segmented into 6 regions, and the color assigned to each region is the final centroid of the color values in the corresponding region in the original image after application of the k-means. I found it very difficult to understand or interpret these images in many papers. They may not describe what is this final color. So this color means that flower has been segmented, and that is the average color of that population of pixels. See, there is some black, light, how should I say? It's pure yellow there, but there is some other color there. So when you average, that's what you get. But the color is different here. The color is different there. Even this is different, of course. But the segmentation, perhaps, where can I show some difference? This rose has red and yellow, but in this method, that whole area has been put together, resulting in this some brownish color. This is what? HSV. Here, the red and yellow parts of the rose have been identified separately, and this yellow flower has been segmented differently. This is not bad. The yellow parts are there. So like that, you compare each one, and this is supposed to be the best. That may not be so bad after all. So you look at that and make your own analysis, but compare each region with the corresponding region. This has averaged out this whole flower with all the white and pink. They're all put together. Here you can see the pink and red and white separately. Okay. So depending on the space that you use, I think the observation is that depending on the color representation space that you use, RGB, sRGB, XYZ, or LAB, LUB, you may get different results. Which one is the best? You analyze and check, and LAB, LUB are supposed to be the best in terms of agreement with the human visual system. That's how they were developed. So the peppers image, they all look good, but that area has been, the dark area here has been identified separately in the LAB. This has averaged out. There's an interesting paper with a biomedical application in histopathology. I'll give the author's name later. This is not our work. Called color deconvolution. In histopathology, multiple stains are typically applied to the same tissue sample in some process. I don't know the sequence of application, but that's what they do. There is hematoxylin, eosin, and DAB combination in this case. In terms of RGB, these are the colors of those stains. So there is this vector P that represents the 3 stains. And then a pixel in the color image of that tissue, every part of the tissue will take up a combination of this. Some will take more of hematoxylin, some will take more of the eosin, and so on. But there'll be some mix. So a pixel Pij, the mean is computed. Pij, it's normalized rather, Pij over this sum of the squares, square root. The color pixel RGB, it's not the whole image, but 1 pixel. Y is Cm. It's like a mixture model. And then you want to get the actual color, Y M inverse. M is the normalized matrix of the RGB values for the dyes. That is, this is normalized. C is Ym inverse. You want to invert the effect of that. So this is what was done by Ruifrock and Johnston in their paper. So this is the original breast biopsy specimen stain with a combination of hematoxylin, which is blue, eosin, which is magenta, and DAB, which is brown. And they wanted to separate them. So each pixel has a combination of these, and by inverting, these are the color definitions in RGB of the stains. Normalize each value here, Pij with this, and that gives you the matrix M of this stain. So a pixel in the given image is Y equal to Cm, and you want C, which is Ym inverse. M is only 3 by 3, so inverting that should not be a problem. So on a pixel by pixel, you separate into the blue, the magenta, and the brown parts. So they can see now, you can see how the stains have been distributed, which parts have taken more of a particular stain when the tissue specimen has been stained with multiple dyes. They call this color deconvolution, which is a very interesting thing. Not image deconvolution, but color. So that is what we have in the book, a quick overview of the book and a few important concepts and some applications, some algorithms. All the color filters, there are so many noise filters, they're all described in the book or in some of our papers. There are a number of other topics: edge detection, region growing, morphological image processing, hyperspectral imaging, analysis of texture, coding, data compression. We did some work. Analysis applications, analysis of burn wounds that Carmen and Begonia have done, skin ulcers that my colleagues in Brazil have done, teledermatology that Carmen and Begonia are doing and have done, telepathology, hyperspectral aerial photogrammetry with LiDAR. That's a big thing. In Calgary, there are some companies, one of my grad students worked for a company doing this, aerial photogrammetry, using hundreds of bands, very narrow bands. So the natural light is broken into 100, 200, 1,000 bands. So each pixel is having 100 to 1,000 values, not 3. So how do you analyze those? You want to separate into various types: building and road and rail and agricultural land and snow and this and that. So that can be done. But then you have to deal with vectors that are much, much bigger. So now instead of calling it color image processing, you can call vectorial image processing. Vector of any size. And the vector could also be multimodal images in medical imaging, CT, MR, ultrasound, whatever. But registration to the same size and geometric mapping will be a problem. That can be done. There are techniques for that. Then you can make one vector for each pixel with all these data. You don't have to display, you analyze them. Vectorial image processing perhaps is a better and generic terminology for this. I missed something. There is another topic, that is, how do you apply transforms? How do you take the Fourier transform for color image? How do you find correlation? So there are some relatively new methods for that. And Jose, who is a colleague of Carmen and Begonia, he's our 4th co-author on this book, the 2nd edition. We are trying to bring in some of these topics, and we have finished 3 chapters, I think, out of 8. So it'll take some more time. We'll expand the book and come up with more illustrations of techniques and applications. So thank you for your attention, and are there any questions about this? Any comments? Easy.
Color can be a good feature.
Yeah. For classification of
Objects.
yes. The problem will be, the reason I put up that collage of so many pictures with the Kathakali dancer and so on, electric wires, when you take a color picture of some scene, you don't know what that color is. This is natural color, but this fabric could be of any color. That color has no meaning there. Even this color has no meaning, but you have to identify the person, for example, and if it is color coded, different types of wires, what is R and what is G and so on. So interpretation of the color in a real life scene would require knowledge about whether it is natural color or simply some paint applied, or is it fabric, some textile, and if it is color on a computer chip, if it is color coding of telecommunication wires, you must have seen all those wires. I have a picture of that going into the computer, and your communication wire channels, they're all color coded. The color may mean something or not. It could be just random, just put this color into that color there when you connect. But a color image could be interpreted, and there are cultural connotations. We have our national flag. The colors mean something. Each color in every flag has been put there to represent some philosophical aspect. So then interpretation of color is a more difficult question. Segmentation, just pixel-based, image-based operations are okay. If you're asked to interpret, then there are many, many other issues that come up. Natural color, pseudo-color, color coding, staining. And
true color? What is true color like?
True color, this is my true color. Yeah, I didn't put any makeup, so this is my true color. And if you look at my retina, that's the true color. And if you cut, what you see is my true color, right? So, yeah, those are true colors. This is nothing. Some objects have the inherent color property, like the green leaves and brown bark or whatever of trees and the patches on animals, those. But then the perceived color is dependent upon the illumination. So true color is what is there on the object. But your captured color depends on the illumination and your detector. And that has to be calibrated if you want accurate depiction or recognition of that color. After going out to some tropical place, when I went back to my office in Canada, they said, "Oh, you got a tan." I said, "This is my natural color. I don't need a tan." Those who have light-colored skin would like to get a little roasted. Like we want the dosa to be ghee roasted a little bit, not too much. So I said, "No, this is my natural color. I didn't get a tan." Okay, we'll stop here, and tomorrow, the first lecture I'll take for about an hour, perhaps less than an hour. I have some general observations. I said radiomics and informatics and all that in the title. I'll talk about that and what is CAD. Again, just a brief generic review of that. No equations, no pictures tomorrow. And that will conclude my talk, and then I'll be off. So if you have any
Okay, so again, it's very difficult to give a talk in the afternoon after the food, as usual. So, yeah. So today we are going to discuss. I'm not going to talk about this. We are going to discuss about this. Okay. So generative adversarial network. How many of you know about this? How many of you know about this? GANs. Okay, so what it does? Basically, what it does? It's a generative model. It's a generative model. It generates the new samples. So we will give a training data, and it tries to understand the structure of the data, right? And then it gives you the new samples, which actually follows the same structure of this, the same structure of the input. So basically it's a generative model, which generates the new images. So first we need to train the generative model, understand the structure of the data, and it understands the structure of the data implicitly. Then it tries to generate the new images. That's the functioning of the generative model. In terms of distributions, right, probability distributions, the generator generates the samples which follows the same distribution of the input distribution. So the input distribution follows some distribution, we don't know that, but generative model tries to estimate the distribution. It understands what the distribution is, and then it tries to generate the new samples. The new samples also follows the input distribution. Right? So the output samples follows the distribution, PDF, same as the input PDF. And what is the difference between this GAN and other generative models that we have in the literature? With this GANs, there is a proof actually. There is a mathematical proof that the generative model generates the samples which follows the distribution, which is same as the input distribution. Other generative models, such as variation autoencoder, it also generates the samples, new samples, but there is no proof. A concrete proof says that the variation autoencoder generates the samples which follows the same distribution of the input. So this is the one model that was introduced by the Goodfellow in 2016 or 2015 I guess. Okay, so today we will talk about this. Mainly the GANs understand the structure of the data. So it's a kind of what it does is it does the kind of unsupervised learning. What is unsupervised learning, right? What do you mean by unsupervised learning? So the supervised learning, right? So what is the goal of the supervised learning? Learn a function. It may be a linear function or non-linear function. Learn a function to map the feature vector to the label. Okay, this is the goal of and the goal of unsupervised. So these are the tasks that you see the supervised learning. So what do you do in unsupervised learning? So you try to find the underlying hidden structure of the data. So this is what exactly the GANs do. The GAN try to understand the structure of the data. So it tries to understand the structure of the data. It tries to estimate the probability distribution that input samples follow. So implicitly, it will estimate the density implicitly. It won't give you the explicit formulae, right? So what are the examples for the unsupervised learning? These are the examples. These are some of the examples which which do unsupervised learning, meaning that these are the methods that get the underlying structure of the data. Another way to get another way to understand, another way to estimate the or learn the underlying structure of the data is using the GANs. So GAN tries to understand, right? GAN try to estimate the density, tries to estimate the density implicitly. It won't give you explicit formulae. So we expect explicit formulae, right? But it won't give you the explicit formulae. It would give you the implicit formulae to to generate, to understand the structure of the data, right? So you can see that these are the examples. This is one way to understand the structure of the data, right? People apply K-means clustering and right, M clustering, many clustering. So this is one way to understand the structure of the data. So another way to understand the structure of the data is, what you do is that you just take the data and project this onto the lower dimension. See, you can see that you cannot understand the structure of the data. But in the lower dimension, you will see that clearly you can understand the structure of the data. You can distinguish the classes here, right? The 4 classes here. But in the higher dimension, you can't understand. So in a way, right? PCA, gives you more structured data. But it's a linear transformation. What does is it takes a sample from the right input space and it linearly takes to the other space. Okay. So you see that there are 3 dimensions here. 1, 2, 3. 3 dimensions are there. Now after you project, and you will see the 2 dimensions here, right? So to represent the data, 2 dimensions are enough. Or you would say the 2 coordinates are enough. So here you have 3 coordinates to represent data, and here you can, right? You can see, right? 2 coordinates are enough to represent the data. So this is one kind of approach where you can see the you can understand the structure of the data. Similarly, the same thing you can see with the autoencoder. So autoencoder also does the same function, but the difference between the autoencoder and the PCA is autoencoder does the nonlinear transformation, but the PCA does the linear transformation. Both do the same thing. Both does the same thing, but it has extra block here. You can see here this is the autoencoder. It consists of encoder and decoder. So encoder takes the input data, and it gives you some representation here at the output. This is called the lower dimension space, where you can see some structure in the data. So from this data you try to reconstruct back. The formulation is different here, okay, and the formulation different over there. Okay. But both do the same same thing, right? So the purpose, of course, this you can use it for generating new images, but with this you get you don't get that much good results. This is a bad generator. The reason is that the encoder only gives you the discrete space. So from the discrete space, if you sample vector and give it to the decoder, it will badly reconstruct. Okay, it's a lossy kind of, it's a right, lossy kind of thing, and yeah, it won't do it. Generally, this autoencoder is not used for generating the images. So the extension of this is a variational autoencoder. So a variational autoencoder is used for generating the new images. So, but this especially this autoencoder is used for for extracting the features. So what you do, right? You just train the encoder and decoder. After you do the training, you just remove the decoder part and take the encoder part to extract the features, the relevant features. But whereas not encoder, what you do after the training, you throw the encoder, you use the decoder to generate the new images. So that's what the same thing we do with the GANs. But what is thrown is we'll see that. Okay. So another way of looking at the structure of the data is you just estimate the density, right? So right, what are the methods available for estimating the density? So we have parametric methods, non-parametric methods, many ways to estimate the density. But these density approaches that we have, right, give you explicit formulas. Okay. So this also, once you estimate the density, right, you with the with those densities you can always test the data using those densities. Right, this is a kind of estimating the structure in the data, right? So next one is this is the traditional methods are already told you that the parametric methods, non-parametric methods. But there is a way to generate, there is a way to estimate the densities using the generative models. So I already told you what is the generative model. Generative model, what it does is they generate the new images. These are the new images. You see here, they are the new images. Right. These new images follows the distribution, which is the same as the input samples distribution. So the aim here is that with the GANs, we wanted to learn a model, right? The P model of X, right? Which is same as the the P data of X. That is the aim of the generative model. So generative model generates the new samples, right? And the generated samples follow the same distribution as this. So basically, we wanted to learn, right, the distribution which is same as the input distribution. So addresses the density estimation. It won't, I already told you, it won't give you explicit formulae, but it gives implicit formulae, right? Implicit in the sense you can generate implicitly. You can see the right implicit density estimation. Okay, so that same thing I have mentioned here. You can see that. So it only does the implicit density estimation, so that you can see here. This is the definition of the generative models. So there are many generative models in the literature. The popular generative models are, these are the three popular generative models, recent generative models, right? This is the one which is the very recent one, which has more advantage than the above two generative models. If you want to know the taxonomy of the generative models, you can find in the book written by Goodfellow. So what the generative model does? What we can do with this? We can do many things with the generative models. We can do the we can do denoising. We can increase the spatial resolution of the image. Right? So we can do we can use these models to generate new images, to increase the data. So many more applications we can see with the generative models. So what is the GAN? What it consists of? What is the definition of the GAN? So this is the definition of the GAN, right? So you see that there are three terms in the GAN, and these are the descriptions about each term in the GAN. So the G means generative, and A means adversarial, and N means network. Okay. So basically the GAN consists of two networks. One is a discriminator, other one is a generative network. These two networks, they fight each other. They always fight each other. I'll just give you a simple example later. I can relate, I can bring the analogy with the example. So first to understand what these two models do in GANs. I already told you that there are two models in the GANs. One is the discriminator, other one is a generator. What the discriminator does? Discriminator discriminates the two classes. Discriminator is like a binary classifier, two-class classifier. It discriminates the two classes. We already studied about the binary classifier. So the discriminator is like a binary classifier. It discriminates the two classes. Okay, it will say real or fake. What the generator model does? Generator model generates the the fake image or fake sample, and it gives to the discriminator. Discriminator says the sample coming from the generative model is a fake, but the discriminator says that discriminator says that whatever the sample coming from the generator is a fake. But the generative model wanted that fake sample to be classified as a real sample. So it says that the discriminator says that whatever the sample is coming from the generator is fake. I would say, right, strictly I would say that whatever the sample is coming from you is a fake. But this guy says, the generative, right, this says, I generate a fake, but you have to take it as a real. So you have to discriminate that as a real. Right? So this is something like, I will give you just analogy for the example. So let's say I am a thief. Okay, I am a thief. Sir is a police officer. Okay, right? What I do, I do mischief things. I generate fake activities, abnormal activities. But Sir tries to catch up that. Okay, right? But what Sir says is that I am thief. So whatever the activities generated from me is a fake. Sir always says that. Sir is a police officer. He knows that I am thief. Right? He knows I am thief. So whatever the activities I generate, he says that activity is a fake. But what I wanted is, as a thief, I generate, I generate abnormal activities. I do the abnormal activities, and I want the police officer to take those activities as a normal activities. If the police officer says that I am fake, then I'll be the loser, right? When he gets lost, if he doesn't discriminate, my activities are fake, right? So I'm a police officer, I'm a thief, and Sir is a police officer. So Sir wanted to become a police officer, I wanted to become a thief. Okay, and that way we get trained, right? So these two models get trained. Right? We get trained. Sir as a police officer, and I'm like a thief. Okay. But after the training, what happens? I don't become a police officer. I don't become a thief. Sir won't become a police officer. That's what happens. This is what happens in the GANs. So after the training, this starts generating new images. So it won't become a thief. It will start generating real images. The discriminator unable to discriminate the sample coming from me, coming from the generator. Then the training stops. So what we have to show is that, of course, we need to show, there is a proof, mathematical proof in Goodfellow, right? what it says is that the generated samples, right? So this generator generates the generated samples which follow some distribution, and that distribution is same as the input distribution. After the training, after it will set, these models settles down, right? What happens is that this generative model generates some samples which has some distribution which is same as the input distribution. So what is that we need to? That's what we need to prove. Okay, mathematically, what people have proven is that they have proven that the distribution of this is the same as that. When that happens, see, if the generator starts generating in new samples, right, the real samples, right, and then the discriminator unable to discriminate. Okay, so what basically what we have to show is that ultimately this is useless, and this starts generating new samples, the real samples. That's what we need to show. When I say the generator, the GANs generates new samples which are of like new samples, which are of real samples, which follows the same distribution as the input distribution. What we need to show is that mathematically is that this generator generates the new samples, and discriminator cannot discriminate the sample coming from this and the real data.
Excuse me. You go back there, please. Is the discriminator acting like a teacher here?
Yeah, like teacher or
To create better and better samples.
no, it only discriminates the two samples. What it says is that the job of the discriminator is discriminate the two samples. Okay, so it says that whatever the sample comes from the generative model is fake. What it strictly says that whatever the sample, it does that. Okay, it does that. In the training process, we get loss function, something like that, and we try to minimize or maximize that loss function. Okay, right? And the job of this is it generates the fake sample, but it wanted the discriminator to take it as the real sample. So when this gets lost, see, there are two losses here: the loss for the discriminative model, the loss for the generative model. When discriminator gets lost, if it cannot, if it says, right, if it says this sample, the sample coming from this is the real, this gets lost. When this gets lost, there are two losses here. So we find the two losses and we combine the two losses, and we try to minimize the losses. So when this gets lost, if this generates a fake sample, right? If the fake sample is classified as fake sample, generator gets lost. This generates a fake sample, and if discriminator says that it's a fake, who will be the loser? Thief will be the loser, right? See, he want he would like to do abnormal activities, and he want this guy to take those as real activities. If that doesn't happen, then this generative model gets a loss. This has a loss and this has a loss, and this is right, we already seen the loss for this. The discriminative model is a binary model, binary classifier. We have already seen what is the loss for this, and we have not seen what is the loss for this. So maybe you can see mathematical proof. So what we do is that, okay, before we see the mathematical part of the GAN, the mathematics would be seen in the Goodfellow book. But however, my student me, I sat together and derived, which is same as that more of, but is slightly different from what you see in Goodfellow. Okay, so I have given the math of that. We have proved that generator the generator generates the new samples which follows the same distribution as this. Okay, after minimizing the cost function. So before that, before we see the mathematical part of the GANs, we see what the GANs try to do, right? So as I said, so this is my distribution of the input. Okay, this is a generator. Generator generates new samples, and you can see the distribution of the generated samples, which is actually same as that. Okay, so ultimately right, after the training, so this would start generating a real like samples. And what the input to the the input to the generator, usually a sample from the normal distribution. Of course it depends upon the application, what you wanted to do. Okay, so right, okay, this is a block diagram of the GANs. So we have a discriminator here and we have a generator here. And what is the input of the discriminator? 2 inputs, 1 input from the real samples and one input from the generator. What is the job of the discriminator? Discriminates the 2 classes, 2 samples coming from these 2. What is the job of this one? The job of this one generates a fake samples, and it wanted this to classify it as a real sample. And if it doesn't that, it gets lost. If right, and if the discriminator says that this is a fake sample, this gets lost. So 2 losses are there. One loss for the generator, other loss for the discriminator. So this discriminator always wanted to do that. They conflict each other. Okay, so they fight each other, but nobody wins at the end. So this guy want to be like a want to be trained like a police officer, but eventually after the training he won't be a police officer and he won't be a thief. Okay, so he won't be a thief means this guy starts generating new samples. So everybody in this.
Finally they understand each other and then do it.
This is what we wanted in society, right? See, if everybody is good, what is the what is the job of this, right? What is the job of police officer? No, nothing, right? So so police officer is useless, right? So that's what right? So this is and you see that the input to the generator is the sample from the latent space, but it depends upon the applications, right? We'll see we'll see one of the applications, which is a vessel segmentation using a GANs, wherein the input to the generator is the input the fundus image. Okay, so we'll see that. Okay, this is one of the study case. So right, the MNIST data. So it consists of different attires. Okay, and we give this is the input data. This is the original real samples, original data, and we give one sample from the real sample to the discriminator. One of the input to the discriminator is from the real samples, and this is the generator. Generator generates a fake sample. Okay, initially it generates a fake sample initially, and then we both we give both to the discriminator. Okay, this is a real sample and a fake sample. Both we give to the discriminator. This is the discriminator 2 samples. So at the end of the training, right, so this becomes useless because this will be exactly like this. This is unable to discriminate between this. Right? We train this as a discriminator, which has to say that the sample coming from this is a fake and the sample coming from this is a real. But what happens is that the way we take up the loss function, the way we minimize the loss function, what happens is that, so ultimately this discriminator unable to discriminate, and this generator starts generating the new model, the real samples. So after the training after the convergence, what would happen? This sample is same as this. The sample that you see here is the same as the real sample. So okay, I'll come to this. This is what happens. This is a overview what happens in what happens during the training. So this is the generator, this is the discriminator, and this is the these are the samples which follow some distribution. Okay, and the output of the generator at each iteration. So at 10th iteration, the distribution of the samples more or less is not equivalent to the distribution of this, but if you see that after 10,000 iterations, somewhat this is similar to this one. The distribution is same as the distribution of this, and the input to the generator is a sample from the normal distribution, standard normal distribution. This is a a latent space. So you usually you give a sample from the latent space to the generator. So this is how you can train. You already know. So what we do, we use the same algorithm, backpropagation algorithm here as well, because we use, so the two models that we see here are the networks, two networks which are CNN networks. This is CNN network, this is CNN network. It need not be CNN networks. Note that these models need not be the CNN networks. These can be any nonlinear models. But usually we use CNNs because CNNs are efficient. Okay, we have the efficient computational algorithms to train the CNN networks. Right. So usually these networks are CNN networks. So we use the backpropagation algorithm to train these. So what we do is that we do what we do is that a particular iteration we may fix the generator parameters and we update the discriminator parameters. In another next iteration, what we do, we fix the discriminator parameters and we update the generator parameters. So this way you can do the training of the GANs. Anyway, now I have the code for one application, so you can see that. I'll forward to you. You can see that. Okay, so now the last function for the GANs is right. I don't know how many of you like math, but we are getting into the math. As I said, so discriminator is a binary classifier. Okay, discriminator is a binary classifier. Okay, so we know how to get the loss function for the discriminator, and you see that loss function for the we need to anyway, right? Okay, this is required. I don't know, this is going like this. I think but some part of the slide is missing. Anyway, right? So this is discriminator loss is this. I don't know how to scroll down. Okay, so yeah, this is better, I think. I guess. Okay, so we know we have already studied the loss for the binary two class binary classifier. The binary classifier. You see that the loss function is this. It's a cross entropy. Okay. This is for this is the loss for the class 1 and loss for the class 0. You combine these two. We already studied some time back. I just mentioned about this. So you just combine this and you get the loss function for the binary classifier. So this is the loss for, you can relate this loss to the discriminator loss. So I already told you discriminator is a binary classifier. It would give you two probabilities. One probability for the real sample and one probability for the real sample and one probability for the sample coming from the generator. So these are the two probabilities. Okay. So using those two probabilities, you can define the loss functions. So here this is a loss function for the class 1, okay, and this is a loss function for the the class class 2, class 0. This is the loss for the the sample which has coming from the generator. Okay, so you see that this is my cross entropy, and if all the samples follows a particular distribution, then you can see that the loss function can be written like this. Okay, so this is how you can anyway, right? So this is about the loss function for the discriminator. Now loss function for the generator. When the generator gets loss, generator gets loss if the discriminator says that whatever the sample coming from you is a fake. Okay. So what the generator wanted is, it generates the fake sample, and the generator wanted discriminator to give one probability. You see here, we want the generator wanted discriminator output would be 1 for the sample generated by the generator. So if this to be 1, then the term that you see here, of course I don't want to I'm too much I don't know.
Plus is there, plus so that you can enlarge this. So that after it is scroll. After that it is scroll.
Oh yeah, here, right, yeah. Okay, so you would see that so this is a loss function that you see for the discriminator. There are two terms here. One term is this, another term is this. So this term is in terms of the generator sample from the generator. Okay, so you take this term and you try to what you have to do is that you try to minimize this. Minimization of this is nothing but getting g of g is 1. Okay, right? So minimization of this is nothing but, right? If if this is 1, what is log 0? Minus infinity. Right? So minimization of this is nothing but making g of g is 1. Making the the probability for the fake sample, right, is 1 by the discriminator. So this is how you get the loss for the generator, and you combine the two losses, right? The loss from the discriminator, loss for the generator. If you combine, then the problem becomes, right, minimax problem. You heard about the minimax problem? Yeah. So the problem becomes minimax problem. If you try to do this, if you try to solve this problem, this would have the solution. Sorry, I don't want to get into too much math, so you require some more theorems, whatever, right? So to say that, I don't want to get into that. So this is very important point here. You can see that. See, the maximum value of that function occurs, at this point, and the minimum value of that function occurs. You can see that if the two distributions, what are the two distributions? If the two distributions are equal, so the min of that loss function occurs if the two distributions are equal. If the two distributions are equal, what would happen is you go to the probability. So d of x is the probability given by the discriminator. So if the two distributions are equal, the probability, the d of x, the probability d of x is equivalent to half. What does that mean is that, what do you mean by d of x is equivalent to half? If this is half, you cannot separate, you cannot distinguish the two classes. If the discriminator says, discriminator gives you half probability for real and half probability for the fake sample, what does that mean? Right? It's not discriminating the two classes. So this would happen, this d of x is equal to half only if you see that we have to have a lot of things here. So that would happen if the two distributions are equal. Okay, so you can prove that. I'll give you the PPT. You can go through that. You will easily understand. But right? You need to understand some probability concepts. Okay, so maybe you can see the Propolis to understand the probability concepts. Yeah. So this is the story of the GANs. So what would happen? This is what happens. Okay. So initially, your data distribution is this, right? And the distribution for the generator, the samples generated by the generator distribution is this. Okay. So this is the distribution of the input samples. This is the distribution of the samples generated by the generator, and this is the d of x. Okay. So after updating the parameters, the discriminator parameters and the generator parameters, maybe it may be something like this, right, after some iterations, right, after updating, right, you have to keep on update that. So finally you see that the two distributions, this may be the distribution of the input samples, and this is the distribution of the samples generated by the generator. And you see that the two distributions are equal, and when the two distributions are equal, and d of x is a constant which is equivalent to half. So this is the proof given by Goodfellow. Okay. So you can find this proof in Goodfellow. Maybe slightly complicated proof you may find, but this is more of that proof only. But slightly I think this proof is much more easier than the proof that you find in the Goodfellow. Okay, so this is the any doubts from till this point? You want me to go to the math, or you don't want the math? See, I just skipped math, but you can always I'll forward you this. You can go through this. So any doubts from the GANs before we?
Suppose we use this process for image generation. They are in the distribution sense, they are same.
Yes. Yeah.
The other perception law, what we are talking about, loss and other things.
Oh.
They may not be exactly equal, so in the distribution sense, those two are equal.
Yeah, there will always be see, if you want to get same distribution, right? So if you want to generate this the sample which is the same as the input sample, so you need to give more training to that, more training data to the generative models. Otherwise, what happens? This what? This may not the error that we have here may not see, you try to minimize this error on the computer, right?
Here on the appearance wise, suppose I have a original image, then I have a reconstructed or generated from this model. There could be a slight.
They're slightly different, yeah. There'll always be like that. See, if you want to get a more exact image, you need to increase the training data. That's the only thing you need to do. And more training data, and you need to run the algorithm till it converges. Okay. So, and in between you should not stop. Okay. So you need to run the algorithm. You need to apply the optimization algorithm till the error error is a minimum error. Okay. Again, there's a lot of problems, right? So we already told you the discriminator is a CNN. Discriminator network is a CNN network. Discriminator uses a CNN network, and also the generator uses a CNN network. Right, the problem with the CNN training of the CNN network, right? We use only the steepest descent algorithm, and right, the steepest descent algorithm tries to give a local minima. It won't give you the global minimum. Okay, so that problem also would be there. Okay. It won't really generate the new images. There will be a slight difference always. You don't get the exact images generated by the generator. So there are practical issues with this.
The discriminator, there is a decision maker, right?
Decision maker, yeah.
The decision maker is CNN or any variety of.
Yeah, any nonlinear model that you can take any classifier which does that, which does the discrimination. Generator does the regression actually. See, generator does the regression and the discriminator does the classification. So this is about the. You already know the application. See, one of the application is this GAN. Can be used to segment the images. So here I have taken the problem of retinal vessel segmentation. I don't know about the fundus image, frankly speaking. Sir knows more. Sir knows better than me. If you want, see that. Okay. So the goal here is to get the vessel part, right? But these are the vessels. Okay. So what we do is that we know, right? The retinal image consists of contains the vast information about the possible diseases. So it's a need of our to segment this. So we give this input. This as the input to the generator, the GANs generator, and we expect the generator to do like this. Okay, this is the segmented part of this. So this is what we wanted to do. If you want to know about the details and all, right, you can ask sir about the. So I don't know about the fundus image, but I'll show you how we can do the segmentation using the GANs. See, it's a simple. It's not difficult to understand. So this is the architecture that you see, which is being used for the segmenting the images. So we have the generator here. This is the generator. And this there are 3 discriminators here, right? Each one handles different resolutions here. There are 3 discriminators here. 3 discriminators handles 3 different resolutions of the images. So we have the ground truth, right? The ground truth from the radiologist or somewhere, right? The ground truth is this, and what we expect generator to give the segmented output, which is same as the ground truth. Okay, this is the ground truth and this is the segmented one. So what is the input to this? The input to this is a fundus image, and the generator is a unit network. Okay, already know, right? We have already studied. You have studied about the unit. The unit architecture. So generator is basically a unit architecture, and this discriminators are basically 2-class classifier. Right? You can achieve with the CNNs, and in addition to these things, you will have some more model here, which is a perpetual loss model. So the input to this perpetual model is the ground truth and the image generated by the generator. So we compute some loss here. This loss also will be minimized. So we have 2 losses here. The loss incurred by this one discriminator, and loss for the generator. Initially you don't get the perfect segmentation, but after the training, if you give more data to this, so you may see, right, the accurate segmentation. You may see that the generated image exactly look like the ground truth. So this is, right, why we want to do like segmentation. Yeah, that right, you can see the sir can answer why we have to do the segmentation. Right? So what we wanted is, so we wanted this kind of image, okay, which must be similar to this. The GAN is capable of generating, right, the images which are exactly same as the ground truth images. This is my ground truth images. So I give the fundus image, and it will give the segmentation of that. So from the segmented image, you can infer. You can take many things out from that. Okay. So you can diagnose the patient based on that. Okay. Or you can do the further processing to get more information about the diseases. So this is one of the application that you find. So this is about the unit architecture. So right, what the unit architecture. This is actually the generator. So this generator is basically the unit architecture. Okay, the unit architecture, right? So it has an encoder and decoder. So here, what the encoder does is that it tries to give you a features image which is a more structured, and from this you try to reconstruct back which is same as the ground truth. So you get some losses here based on the ground truth, and you try to you try to update, you try to modify this based on the ground. So this is what. So this is a perceptual loss, and this is the code. Okay. This code implemented by my student. This is one of the assignment for my coursework. So once one of my student implemented this. So this is the code. If you want the code, you can approach me. I'll give you the code. So this is the this is the details of the discriminator model. So you can see many convolutional layers and batch normalization layers, and many things are there. So at the end we use the dense layer to classify the 2 classes. So there are this particular architecture uses different discriminators because we need to, it is why, this is this architecture from one paper. They used three different discriminators to handle the multi resolutions. So we don't know why they have taken that. So we have just the students just has he has implemented the paper, and he has used the three discriminators over that to handle different resolutions. So this is the code. You can see this. So that this about the GANs and its application in medical imaging. So any doubts on this, you can just but mathematical part, if you want me to explain, I will explain, but outside, okay, not here. It consumes a lot of time to explain. So if you have any doubts on the functioning of the GANs or the idea behind this, so you just write
What are the performance metrics used to evaluate the GAN network?
performance. Yeah, it has to, like, the generated image should be matched to the real like samples, right? So if it doesn't, then there will be error. We get the loss right there, right? So we try to minimize that. So metrics you are saying, right? So you have to compare with the always the real samples. No, you can use what you're saying. I didn't get you exact question from you. Maybe you can use the similarity index, right, for evaluating. Maybe you can. Yeah.
In the case of the retinal images you showed for the drive and stare images, the ground truth is given, so you can compare with the ground truth of the vessels marked by ophthalmologists.
Yes, correct. Yes. Yeah, you can do that. Yeah. Yes, correct. So you see that exactly, right? We see that we use. See, this is to compare. See, we use a Jensen inequality. So this would give you right. Of course, this is to compare the two distributions. So overall, you would see that we need to minimize this, right? The minimum value, this is a constant, okay? And the minimum occurs, right? What is the minimum value of this? The minimum value of this is 0. This happens if the two distributions are equal. This is called the, this is similar to the Shannon divergence. KL divergence. This is again from the information theory. So you need to know a little bit about the information theory to understand this. Okay. So and we can, of course, there are a lot of mathematics behind this. So we have used some identities here. You can see here. So this theorem, right, from the probability theory. So this is the theorem that we have used to prove the the two distributions are equal. So we know, right, if the PDF of random variable is G is given as this, then the PDF of another random variable, which is a function of that random variable, right? So the PDF of the this random variable is equivalent to this. This you can find in the Papulis book. Okay. So this identity, this theorem we have used to manipulate the objective function, and we have rewritten the objective function so that we can proceed further. Okay, so we have modified this one, and then but a lot of understanding is there. So you have to I don't know, you need to have the background of probability. Okay, unless you have that, you don't understand what is happening there. Okay? But the functioning definitely understand. Okay, see, if you want to know the proof, right, why the two distributions are equal, then you need to understand the loss functions and the minimization of the loss functions. So this is what Okay.
But I will share two small stories, but I'll do that after you close the recording.